Report to the computer, is that
Yes.
Yes, to the computer. And then Cheris, just for everybody to be aware that we can hear the teacups and everything. So if they can avoid those also.
I'll tell them they're not allowed to have any coffee.
So if that's sensitive.
Morning, everyone. Prof. Maya, are you with us? Prof. Maya? Prof, are you with us?
Good morning.
How are you doing?
I can't hear you. So I need an indication that you can hear me. It's Professor Meyer.
We can hear you, Prof. We can hear you perfectly.
Good, thank you.
Right, so good morning, colleagues, those that are here, and the team that is online. Welcome to our workshop on data science across disciplines. We are actually quite happy as the Department of Maths and Applied Maths, with the help of the Faculty of Science and the Research Office, to host this particular workshop, which is basically in two parts. Either you are here with us in the room, or you are somewhere across the world. So I want to welcome the Dean of the Faculty of Science, who will give an opening address. Professor Meyer, welcome, and I'll give you the platform to just welcome the participants. Thank you so much. I hope she had.
Thank you, Professor Hali. I hope all of you can hear me because I could not hear Professor Nyabadza earlier. So before I get started, if somebody can just indicate to me that they are able to hear me.
You can, Prof.
Professor Ali, can you confirm that you can hear me?
You can. Thank you so
Good.
much.
Thank you. Good morning, colleagues. And welcome to this workshop. Thank you very much to Professor Nyabadza for giving me an opportunity to welcome all of you this morning. I hope that you will have a productive workshop, because as the Dean of Science, for me, it's excellent news when workshops are being held so early in the year, because it means we are making a running start into achieving our goals for the year. From what I understood, there's also people logging in from different spaces. So Prof. Nyabadza, keep in mind that this can also be part of our inbound, outbound concept that the university wants us to focus on. But welcome, colleagues. I'm glad to have you all here, active in the new year. And I think every one of us celebrates the fact that at the moment, South Africa seems to be doing quite well with regards to the Omicron variant of COVID-19, while the rest of the world is having a tougher time. And I think part of the discussions you're going to have this morning is actually why we are doing so well. In the past 2 years, the role of science in decision-making and influencing policy direction was clearly evident in the fight against COVID-19. The role of mathematical modeling in predicting the cause of the current pandemic was and still is highly important. And I am delighted to report that a number of researchers from UJ have been actively involved in the modeling of COVID-19 and other infectious diseases. And this workshop is an indication that the work will not only continue, but will expand. And it's vitally important for our country, the continent, and perhaps even the world. During the same period, a lot of data has been collected, meaning the past 2 years, a lot of data has been collected and continues to be generated. This data has been the subject of discussion with respect to its accuracy, usefulness, and storage. The linkage between infectious diseases and data is the subject of the workshop and will focus on data management and ethics, dynamical systems, and parameter estimation. UJ has pioneered and continues to champion the fourth industrial revolution. Coupled with that is the potential application of machine learning and artificial intelligence in the management and control of infectious diseases. In collaboration with the data science across disciplines, Research Group, and the National Department of Health. The Department of Mathematics and Applied Mathematics at UJ is the host of this study group on disease modeling using mathematics, machine learning, and artificial intelligence. And the objectives of the group, as I'm sure many of you will know, are to introduce and strengthen research in machine learning and artificial intelligence in health. Also, to dramatically increase and sustain research collaboration between African researchers in health, and of course, to improve collaboration between South African and other African research institutes and universities. And I'm sure all of you will agree that these objectives, if they are achieved, holds great benefit for South Africa and the African continent. The Faculty of Science continues to actively support initiatives that are strategic to UJ, and this is one such initiative. We've mentioned to you that UJ considers itself the University of the Fourth Industrial Revolution, and its disciplines like mathematics, statistics, computer science, and informatics, where we expect the new developments to come from that will keep us on the trajectory of being a leader in the Fourth Industrial Revolution. So with this workshop, you are all starting this year on a very productive note, and of course, very much focused on the key performance areas of the university, the department, and the faculty. And I wish you the very best in achieving your goals of strong collaborative research and the publications and student training that must be part of it. So Professor Nyabadza and the group who organized this, I commend you on doing this, not only hosting the workshop, but doing it as early in the year as possible, that then sort of sets the stage and sets the tone for how the rest of the year will go. So I wish you all the best, and I look forward to a report from Professor Nyabadza of the success of the workshop. Thank you very much, colleagues, and all the best for the day. Professor Hali, I give the microphone over to you again. Thank you.
Thank you very much, Prof. We really appreciate your time and for opening up this workshop for us at quite an early hour. For those of you that are online, please just take note what Prof. Meyer was referring to. I put something in the chat. If you could please just type on the link and just give us a sense of your presence here today, that would really be very helpful. Our next presentation is going to start at 9 o'clock, so for the sake of those that are still going to join us, I would just like to give us a few minutes. Please go get a cup of coffee, and we'll be starting with our first presentation today, which will actually be presented by myself. So we'll see you in a bit.
Yeah, instruction to come.
Capture app is the easiest way of recording musical ideas and collaborating in real time.
Morning, everyone. Can somebody just give me a thumbs up that everybody can hear me, please, online? Thank you. All right. So I think let me just first introduce myself. My name is Shrees Harley. I am a professor in the Faculty of Engineering in the built environment. I run a research group, data science across disciplines in the Institute for the Future of Knowledge, and we're actually co-hosting this workshop today on infectious disease modeling through mathematics and machine learning. I think this is an incredibly important workshop, not just because of the context, which is obviously very relevant today, but also because of the fact that it shows the link between these two different fields. And I think sometimes people tend to forget that there's actually a lot of overlap, a lot of important overlap, in fact. So the aim of this workshop, in actual fact, is specifically focused on postgraduate training. So the way that the workshop is functioning is that for the first week, those of you online will be joining us in the mornings for our presentations, but in the afternoons, for those that are actually they'll actually be taking part in the practical sessions where we'll actually be providing them with different kinds of worksheets, different kinds of forms of engagement. And the second week, for those of you that are here, we'll actually be presenting you with real life problems that we want you to solve with all the methods that you've been learning this week. So I think hopefully those of you online as well, but mainly the people that are here, you'll actually walk away with a lot of new knowledge, deeper understanding of the variety of different kinds of methodologies that can be used in the field, and hopefully that will be of benefit to you. So today's presentation, they are, to start off with, a variety of different kinds of resources. These are two main ones that I've worked with, but there are many, as you'll see, going throughout my presentation. Currently, in an age of knowledge and information transfer, there are so many different kinds of resources to rely on. So if there's any kind of new idea, anything that you want, there's information out there to find. And I would advise, in actual fact, and you understand this also as I go through my presentation, that you not just focus on one resource, that you actually use them to understand each other, and that you also make sure that you gain more sophisticated understanding of different kinds of resources. So I think the first question that comes up when I work with most of my postgraduate students in the field is that when they start off doing this thing called an exploratory data analysis, it kind of comes down to, well, I just feel like I'm cleaning data. I feel like I'm just like removing like empty spaces, or I'm just removing names, or this is not very interesting, like I'm plotting stuff, but I don't know what I'm looking at. And the reality is that when you're conducting a proper exploratory data analysis, your aim is not just to understand the data, but in so doing, actually be able to then employ it in a mathematical model, machine learning model, whatever it might be. But the reality is that the data in its raw format is not useful. It needs to be structured in a manner that actually becomes useful to you. So, and that takes time. In actual fact, in a lot of these kinds of problems, many people will tell you that the initial phase of cleaning, working, understanding, exploring is the longest part. It can take a very long time. I've sometimes spent days just looking at the data before I even did anything to it, just to try and understand. And I'm pretty sure if you've done any kind of work with industry and companies, the data doesn't look as nice as it does in CAD. Let me put it that way. So they'll often give you stuff and there's repetitions, there's redundancy, there's errors. And this is basically the kind of process that you need to go through. As a warning, this is a small portion of what exists in the field of conducting an EDA. In essence, you are drawing from statistics, mathematics, data visualization techniques. You actually end up using unsupervised machine learning for your feature engineering. So you're pulling from so many different kinds of fields in order to have a process that you could follow. And this is just a small portion. There are so many tools out there, and people have created very interesting combinations of tools in order to be able to gain deeper insights. So this is a starting point, and only that. In essence, you can just never stop reading. That's what it comes down to. So as we all know, data comes from a variety of sources: files, databases, sensors. And the reality is that when you collect it, often it's unformatted, real-world data. And that's where your data preparation comes in. So, and this includes your data processing, which means that you're converting this raw data into a clean format, which is then in essence useful. And there's a whole process that you need to follow through, and we'll go through that. Then there's also the data wrangling component, which is in essence what you start doing when you actually want to incorporate this into an interactive model. So that's when you want to make this useful for machine learning. And you'll notice that even though you can do certain kinds of analyses and you can understand certain things, it doesn't mean that the data as it stands can be used in a machine learning or mathematical model. So now some of the other features that also affect what comes down to, in essence, your data quality is your timelines. So is the data complete? If you've got a data set that you've been given and then suddenly more data gets added, you often have to start from scratch, because the reality is that you don't know to what extent this additional data will completely influence what you need to do. Then believability. So is the data actually trusted by the user? So when you create a model or a machine learning model, whatever it might be, right? This is going to a user that's going to implement this in some context. And if they don't trust the data, if you don't trust the data, that's a problem. And this is the kind of thing that needs to be investigated. Then interpretability. So I think many people have started hearing a lot about explainability, interpretability, and that in essence comes down to the fact that when you've used your data, especially in a black box context, which even mathematical modeling has become for many people, it's something that's not always tangible because it can become so complex. Do you want to be able to at least be able to say to the user, look, these kinds of features, this kind of data, it makes sense that it led to this, whatever that outcome is. And so you want it to be able to be understood by the stakeholders. So one day when you present, if you have somebody who has a lot of domain knowledge and they put up their hand and say, why that feature? Why that data? You need to be able to understand that and you need to be able to explain. So under the heading of your data processing, data cleaning is one of the things we're going to focus on first before we even get to the the EDA. But you'll notice there's an extreme amount of overlap. In many ways, when you're exploring your data, you're also cleaning it, you're also restructuring it. In essence, the important thing here is for you to gain the data quality that you want. So you're looking at techniques that focus on removing your outliers, replacing your missing values, smoothing out the noisy data, correcting inconsistencies, finding errors. And there's an essence of process that you follow, a workflow in essence, to be able to get this high quality data that you want. Inspection, and this can take a long time, depending on this data set, the complexity of it, where you're basically trying to detect your unexpected, incorrect, and inconsistent data. And don't underestimate how much that can influence the quality of any predictions or classifications you're making. Then you need to clean it. You need to fix, remove anomalies, remove irrelevant data, duplicates, make sure it's in the correct format. Does it need to be normalized? Does it need to be in a different kinds of metric? What is necessary within the context? And then verify. You need to verify your data. So there needs to be some kind of mechanism that you implement to check that what you've done hasn't completely restructured your data or completely lost information that you actually needed. And then the reporting process. And this is, for me, I think sometimes often overlooked. It's extremely important that you have some kind of process in place where you're in essence reporting or keeping track of what you've done. So I often, when I'm doing an EDA, and you'll see also when you do the worksheet this afternoon, we're working in Jupyter notebooks, and you'll notice that what I'd like to do is I actually keep track of every single change that I've made inside my notebook. So if there's the original data, then I say, this is the next thing I did, this is the next thing I did, this is the next thing I did. I removed this, I removed that, I added in this. And it's just mainly because at some point I'm going to go back and somebody might say, but why does the data now look like this? And I have to be able to justify. So there are 5 main factors, I would say, that contribute to your the quality of your data. Firstly, it's your accuracy. And this basically is just how accurate how close is your data to the actual true value. And there are a variety of different issues that can come into play. You can imagine human computing error, if the error is actually, so for instance, if it's interviews, that data is manually probably being loaded. There can be many errors can crop in that way. Sometimes users deliberately submit incorrect values, right? For whatever reason, they weren't paying attention or they just didn't care enough, variety of different issues. Incorrect formats for input fields. So sometimes you open a data set and there's a whole bunch of question marks or something coming up because the format was incorrect and so the file can't be read properly. And then duplication. That can also often happen, especially if you think of somebody who's doing this manually. they can by accident duplicate a field. Then there's completeness. Now this is a big issue, especially depending on the context in which you're working. Where basically you want to have all the different kinds of data that is important. So if you're lacking a specific kind of attribute or a feature, that can be a concern. It can completely influence to what extent you might have an effective model at the end of the day. So you can have missing values and NaN values. For instance, the financial data, sometimes it doesn't get recorded on the weekend. So you'll notice every 5 days, there's like 2 NaNs popping up. And the question is, like, there's obviously a difference from Friday to Monday, right? The market doesn't like completely stop functioning, but that's the kind of thing that you then need to be able to take into account. Deletion of inconsistent data. So if you've got a feature saying one thing, something saying another, even within a variable, if there's something that's inconsistent that doesn't quite match, you need to actually be aware of this. And then the deletion of data that initially seemed irrelevant. So we're going to discuss what is called multicollinearity, which basically means that there's a strong dependency between two variables. And the idea is that once you assess this, then sometimes you remove this data because you think it's not relevant, it's not adding value. At a later stage, you might discover differently. The inconsistency, you need your data within a data set or across multiple data sets, depending on the problem you're looking at, you need to be consistent. So for instance, if you have data sets that contradict each other, so if you're looking at aggregation of data, for instance, is inconsistent to the actual data itself, that can also be extremely problematic. And then uniformity, so the degree to which your data is specified using a specific unit of measure. You don't want something to be measured in meters, then suddenly in centimeters, then suddenly in kilograms. That's going to be problematic. Then your validity. This is particularly important if you're working within a specific business constraint. So there's specific business rules that are being put in place. So for instance, values in a particular column might have to be of a particular data type. You might have range constraints. So if a variable is supposed to exist within a certain range, and all of a sudden it's sitting outside the range, that's a problem. There might be certain kinds of constraints. For instance, certain columns can't be empty. If that column is empty, it then leads to some kind of inconsistency within the data set itself. There could be unique constraints. For instance, a field or a combination of fields must be unique across the data set. Otherwise, that causes specific kinds of problems. You can have membership constraints, where basically the values of a column need to come from a specific place. Foreign key constraints, so for instance, in relational databases, where a foreign key column can't have a value that doesn't exist in the reference primary key, right? Regular expression patterns, so text fields that have to be a certain kind of pattern, so they have to follow a specific kind of formatting structure. And then cross-field validations, so certain conditions that basically span across multiple fields that must hold. And all of these different kinds of things, for you as the data analyst, you do need to be aware of. Just because somebody's giving you a data set, it doesn't mean you can say, oh, okay, it must be fine. They must have taken all of these things into account, because they haven't necessarily. So, then your data integration. So in practice, you'll notice that your data is coming from multiple different sources. And at times what there needs to be happen is that this data needs to be consolidated, it needs to be brought together. And you need to make sure that it's not redundant and it's not inconsistent. So your data consolidation, either this can happen in data warehouse, data lake, variety of different ways in which it can be done. You can copy data over from one location to another using different kinds of applications. Data virtualization, so we have some kind of interface that brings it all together. But at the end of the day, one of the things when you actually start working in industry, for instance, is that these kinds of processes have various kinds of pitfalls. And you, as a person that's going to be working with the data, you do actually need to understand where your data is coming from. Is there any chance that something could have been neglected? Any chance that something could have been forgotten or lost? So that's just a kind of like a context within which your exploratory data analysis is happening. So the reason why you need to be aware of these different kinds of components is because they can very much influence the quality of your data analysis that you conduct. So now let's actually get into what it is that you will be doing as the data analyst. Hopefully your data set is not completely crazy and looking absolutely horrible. Hopefully there's something that you can actually work with. So first things first, variable identification. Make sure that you understand what are your input features Because remember, you're working with a model. So you have certain data features that go into the model, and then you have the target, the thing that you're trying to predict, the thing that you're trying to potentially classify, whatever it may be. I once worked on a project where it took months for the person I was trying to conduct an analysis for to finally explain to me what his target was. I don't think he understood what his target was, and so he made it impossible for me to understand what his target was, and then the entire model had to be redesigned from scratch again. And that's the kind of thing that you do need to be aware of. And then you need to understand the data types and the categories of your variables. So for instance, you've got your predictor and you've got your target variables. This is just an example, right? But then you've got your data type. So is it a character, student ID, gender, for instance, or is it a numeric value? So whether you're playing like crickets, or for instance, if your previous exam marks, your height, your weight, so a number. And then your variable category is then very important, completely influences the kind of analysis that you conduct, the kind of statistical measures that you implement. So it is categorical, i.e. it's a character, and then continuous, i.e. numerical. Okay, so let's start off with your categorical variables, right? So these are basically data streams, and they're not continuous. So they can be subdivided into three main parts. Your binary or dichotomous, so these are just like yes or no's, true or false, okay, two options. Your ordinal categorical variables, so these variables can be ordered, so medium, large, extra large, and this becomes important, and so you need to understand this. Then your nominal categorical variables, they can't be ordered, but it's like, for instance, a color, so blue, red, green, for instance. And each of these gets handled in a particular way, especially when you're starting to use them in a machine learning model. Then your continuous variables, so these are basically quantitative variables, and you're looking at an interval variable, for instance. So this is just a continuous variable. It's considered an interval between two numbers, and it has fixed values between these 2 points, but it doesn't have a meaningful 0 point. Now, what that refers to, let's go to ratio variables. It actually explains it much better. So ratio variables are interval variables, but they have a 0 of the measurement. So it indicates that there's literally none of that variable. So if you're looking at Fahrenheit and Celsius, for instance, 0 degrees Celsius, it doesn't mean that there's no temperature, it's just a 0. Whereas temperature measured in Kelvin, for instance, is seen as a ratio variable because 0 Kelvin, which is the absolute 0, basically indicates that there's no temperature at all. So it's that differentiating feature between the two. Now, there are certain important considerations to take into account that you need to be aware of as you analyze it. All right, we're going to start talking about a univariate, bivariate, multivariate analysis after this, but there's certain things that I think are extremely important. And one of those is multicollinearity. Now, this can occur in your data set when you have features that are strongly dependent on each other. So they have high intercorrelations among what you would have thought would be independent variables. So it basically means that one predictive variable can be used to predict another, right? And this information can be so embedded in the feature in your data set that you aren't aware of it. It can basically lead to redundant information, so skew the results. And remember also, if you have redundant information, if you have a larger data set than you need to, that has certain consequences, right? In terms of computing time, just in terms of managing the problem easier. And it also may shift your decision boundary. So when making decisions on classification, for instance. So to identify multicollinearity, a very simple way is to just plot a pair plot. So basically, if you see a linear relationship between these features, then they're strongly correlated, and it's likely that there exists multicollinearity in your data set. Then your balancedness and your sparsity. Now, this is important to consider because it will impact on the kind of predictive classification or clustering algorithm that you'll be employing. So your balancedness or unbalancedness basically comes down to the missing observations that you have. And there's in essence, they are two kinds. So if it doesn't contain a time variable, then it's considered balanced if each feature contains the same number of observations. Then you balance. So a very easy example, which everybody's aware of, is credit card fraud, for instance. Most likely or not, it's when you have a transaction, it's not credit card fraud. But there is a small likelihood that there is, and that's often a very unbalanced data set. When you do have a time variable, though, then your features are said to be strongly balanced if each feature basically contains exactly the same time. All right, so you're functioning across the same time range. It's weakly balanced if each feature contains the same number of observations, but not across the same time points, and then otherwise it's seen to be unbalanced. Then there's also sparsity. So variables seem to be sparse, basically, if there's a relatively high number of variable cells that don't contain actual data. So such as like empty or not applicable or unknown. And there are two different kinds of sparsity. There's the controlled sparsity, which occurs when your range of values of one or more dimensions has no data. So it usually happens when a feature only starts to exist at some point in time. And that often does happen. And then obviously you have to decide how you're going to handle this data set with these features that function like this. And then you have random sparsity, where these NA values are basically scattered throughout the data set. And it's usually sometimes just because certain instances don't exist, or certain kinds of dimensions just don't exist for that specific kind of data. And then there's the missing values treatment. So you've got a data set, might be sparse, but either way they're missing values, and there are particular ways in which you can treat these missing values. Now, depending on your data set and your context, different kinds of options are better than others. And this is where working with somebody that has domain knowledge can be extremely important, because just randomly dealing with these missing values, not understanding what you're doing, completely change the nature of your data set if you're not doing this properly. So reasons for missing data extraction. So basically when the data is extracted, it's possible that that didn't work well. So it's a good idea to actually check with whoever's assisting you if you're not doing it yourself. Then data collection. As you can imagine, when data is collected, at the time of data collection, then that can be problematic. It's also more difficult to correct, right? Especially if it's something that happens after the field. So these kinds of values can be missing at random. Maybe it was just unobserved predictors, so there was nothing to observe, or it depends on the specific missing value itself and the nature of it. So how do you treat these missing values? So there are a variety of different options. I'm pretty sure that this is not an exhaustive list. I'm pretty sure there are about 40 million other kinds of options as well, but these kinds of ones are just most prominent. So there's deletion. You can basically delete those points. And sometimes this is perfectly valid and you're not losing any kind of information. But you need to be careful because you might be losing something in the process. So deletion methods are usually used when it's happening at random. So when you basically have these random missing values that you don't know how to deal with. When it's not random missing values, then it can bias the model. So this is why you need to be very specific and very aware of what it is that you're doing. Then there's manual replacement. This can be very time consuming, but if you have a small data set and you really understand the context in which you're working, this is actually a very good method, I would say. But this again, domain knowledge becomes very important here. Then standard value replacement. So basically when you're just adding in an NA or an unknown, and if your analysis can handle it, then that's fine, but it's also again not foolproof. Then your mean, mode, or median imputation. So imputation is basically just providing some kind of an estimate. So you want to basically employ like the known relationships that exist within your data already, and then use it as a way to kind of estimate that specific point that isn't there. So generalized imputation, for instance, is when you're replacing the mean or the median with values for all missing values in that specific variable. So you're basically just taking the mean and you're just plonking it in everywhere where there's a missing value. Similar case imputation is basically we're doing it within a case type. So for instance, if you're looking at the average weight across men, then that's the average you'd place there, and then do it separately for females, for instance. Then you have imputation methods. So this is actually where you start using machine learning methods to be able to do this. So using k-nearest neighbors or whatever kinds of value you want. But you can also, if you just think of like what you would have probably learned in mathematics and applied mathematics, using a spline, using basic linear regressions, the same kind of concept here. And then also a prediction model, where you basically create a predictive model to estimate the values that will substitute the missing data. So the model estimated values can often be more well-behaved than what the actual values would have been. And if there's no relationships with attributes in the data set, and there's an attribute with missing values, then the model won't be that precise. So this is again where you kind of have to play around and just see what works best. Then techniques for outlier detection. Outliers can be extremely important, but also tricky to handle depending. Sometimes your outliers actually provide you with more understanding of your data set. So just randomly removing them, which I think is often the immediate intuition, might not be the best way. In actual fact, sometimes the focus of the work is specifically your outliers. So just be very careful with this. So outlier can be of two types, univariate or multivariate, and they're different ways or reasons why you might have these outliers. It might be artificial, or it might be a natural outlier. So this is a legitimate observation. And it's important to note to what extent important information is basically inherent in these data points. So that because those outliers can drastically alter your analysis. And often visualization techniques are used to be able to identify them. So block plot, histogram, scatter plot, which we'll get to it in a little bit. So those are often the easiest ways to just identify them. But there are also many other ways in which analysts have actually been able to detect outliers. So you basically create some kind of measuring structure, whether it's within minus 1.5x to 1.5x of the interquartile range, whether you're basically saying it's out of the range of the 5th and 95th percentile, 3 or more standard deviations away from a mean as considered outliers. They can also just be seen as like a special case. So you can just see this thing that is special and it's just completely standing outside. But basically, in essence, what you're doing is that you're looking for some kind of measuring device that in comparison to what is in essence your normal data set, what is looking different? What is other? And sometimes there's not a big difference, but the difference is tangible enough for you to be able to say that must be an outlier. So removal of outliers. So the most of the ways that you would deal with them are similar to the methods we employ when managing missing values. All right. So you can delete them, transform them, bin them, where you basically bin your data so that you're pulling them into the rest of the data set. Treat them as a separate group. So those are the different kinds of methods, but there are a variety of different statistical methods to be able to deal with your outliers. So when you delete your observations, you're basically saying, you know what, these outliers are adding too much noise. They're not really helping me understand. I'm just going to remove them. Transforming them, this can help you eliminate them. So for instance, the natural log of value reduces the variation caused by these extreme values. And binning is another option that we're going to discuss. Decision tree algorithms actually allows you to deal with outliers very well, specifically because of this binning characteristic. Then imputing, so estimating the value in a different way. But you need to then understand whether this is a natural or an artificial outlier. If it is artificial, then you can go with imputing, so just estimating values. But you can also use statistical models to predict observed outlier values. And then after that, you can impute them with predicted values. And then you can treat them separately. And sometimes this is actually more meaningful, depending on the nature of the problem, where if there's a significant number of outliers, then you basically treat them separately with a different kind of statistical model. And you treat both of these groups kind of separately, and then bring all of that output together at the end for increased understanding. And now noisy data. Noisy data is basically defined as a random variance in your measured variable. And similar to how you would deal with your outliers, you're basically looking at data smoothing techniques, whether this is your binning to smooth these kinds of values out, regression. So you can use linear regression and multiple linear regressions actually to smooth the data. So the values conform more to the rest of the data set. And then you have your outlier analysis, which we just discussed. So basically we start thinking of those noisy data within the context of an outlier analysis. So you're looking at clustering that can actually separate these outliers, which is actually a very useful technique. Now, understanding your data. So all of this in many ways is precursor to the actual analysis as we understand it within the context of statistics. I would advise if you really want to be comfortable with conducting an exploratory data analysis, that you go back to your stats. A lot of the techniques here, they come from statistics. And obviously, new techniques are constantly being created and being developed. And obviously, the better understanding you have of these various techniques, the more you keep up, the better you'll be at being able to conduct an analysis of this kind. So, univariate analysis, this is where you're considering your variables one by one. And you're looking at your variables as categorical continuous. And the reason is because the kind of analysis that you implement for either one is different. All right? That's why this initial variable detection identification is extremely important. So for instance, if you're looking at continuous variables, your histogram is an excellent way of understanding your variables. So it's a representation of the distribution of your numerical data. So it's an estimate of the probability distribution specifically for that one continuous variable. Right? You'll notice later on we start looking at the one. So here you can see examples of how your histogram can actually help you understand your distribution, whether it's symmetric, unimodal, skewed to the left, skewed to the right, multimodal, whatever it might be. Basically, your histogram can just give you that snapshot of what is happening with your data for a specific kind of continuous variable. But now there are important tips to remember, right? And this is where understanding the actual statistics, so the actual method and what it's doing and how you are implementing it is very important. There's a huge tendency these days to kind of just throw your data at methodologies, to throw your data at Python or MATLAB or R or whatever it might be, and then whatever pops up, you're like, that's good, okay? It doesn't work like that. You as the human, the reason you get hired is because you are that interface, you are that in-between, you are that person that understands these methodologies, you understand the implementation of them, so that you can ensure that there's a level of accuracy and there's a level of sophistication that comes to that. And then you are the one that basically, you're the quality checker. You're the one that in the end puts that tick and says, this is good. All right. So histograms must be plotted with your zero value baseline, because if you change that baseline or introduce an artificial gap, then you're skewing the perception of your data. The number of bins and their sizes must be chosen by either playing around, but also introducing that domain knowledge. Because your choice of your bin size, for instance, has an inverse relationship with the number of bins. So if you have too many bins, for instance, then it's difficult to discern what is noise and what's the actual signal. So if you look at the bin size on the left, there's way too many bins. So the bin size, the bins are way too small. So it's looking a bit all over the place. If you have too few bins, then it leads to a lack of detail. So if you're looking to the right, the bins are too large. And so what's happening is that you're missing the second peak that you can see in the center there. So this is the kind of thing where you actually need to engage with your analysis, look at different options. Make sure that you actually go to a domain expert and say, look, I got this, does this make sense? And then within the context of your work environment, you'll gain that domain expertise as well, which will make you so much better at conducting such analysis. Then we have box and whisker diagram plots. And this shows you the distribution of your quantitative data in a way that actually facilitates comparisons between variables, which is extremely useful. It allows you to assess the variability or the dispersion of the data, where you're looking at the quartiles of the data sets. All right, so in essence, what you're looking at is a box plot. It's looking at a five number summary. So you're looking at your minimum, your maximum, your first quartile, third quartile, and then and you've also got your median. All right. So in the center, you've got your box. You'll notice on this image, it indicates your 25th percentile, your 75th percentile with your mean. And then your whiskers are basically providing you with your minimum and maximum. And this is where you start also getting a sense of what kind of outliers you have, which is very, very useful. It can also tell you if your data is symmetric, and then also how tightly your data is grouped. So this is a very easy way to, when you're looking at your features, as in this graph, you actually can start seeing, there's similarity, or wow, there's one feature that's functioning in a very different manner. Then there's the kernel density estimate. And this estimates the probability density function by providing you with a smooth estimate there. So it's using all the sample point locations, and it more convincingly will suggest the modality. So here is an example, for instance, where different kernels are used. So you can use a Gaussian kernel, top hat, whatever. But as a consequence, you can see how you can then look at your data and get a smooth assessment of the PDF. So it's basically useful for plotting the shape of your distribution. It allows you to check for the linearity of the variables and then the skewness of your features as well. And this actually particularly belongs to a class of estimators called non-parametric density estimators. All right, so when you start going through your first year statistics, you'll start remembering that there's parametric versus non-parametric methods. So parametric estimators is where the estimator has a fixed functional form, and the parameters of this function are the only information that you basically need to store, like your mean and your standard deviation, for instance. Whereas with non-parametric estimators, they have no fixed structure, and they depend basically on those data points to reach your estimate. Okay, so those are your continuous variables. Next, we're looking at your categorical variables. Very different. I think these are the kinds of graphs people are very, very comfortable using. I think in every single presentation I've ever seen, there's a pie graph and a bar chart of some kind. So firstly, you've got your frequency tables, just to help you understand the distribution. So this is just looking at numbers, count to count percentage, and then your bar plot. For those of you in the afternoon session, this is actually the kind of data set that you'll be looking at this afternoon. So now you've got a bivariate analysis. And when this is happening is we're basically looking at two different kinds of variables. So you've got your continuous, categorical, and then obviously categorical and continuous. And you want to understand the relationship between these two. So association and disassociation between these different kinds of variables. And this can be extremely useful. Even if you're then also starting to create, when we discuss the multivariate one, pulling in your target variable with these kind of input variables. So if you're looking at two continuous variables, okay, a scatter plot is very basic, but it's very useful because the pattern observed from a scatter plot indicates the relationship between these two, linear, non-linear, and understanding that alone can help you unearth the dynamics of your data set. So the thing about scatter plot though is that it can give you a sense of a possible relationship between, for instance, your feature and your target vector. So we're not just talking about your features, so the input data, we're saying you can do this with your target variable as well. i.e., is there like no correlation between your target and one of your features? Then you need to start wondering, like, why is this feature here? Is there a reason for it? But if you want to find the strength of that relationship, then we're talking about correlation, all right? And this is where especially a lot of your stats is coming back to you. So you're looking at your correlation varying between -1 and 1, and you can see here that just the top plots at the top, very different kinds of relationships coming about. Top left, basically no correlation. Then the plot next to it, you start seeing a small negative correlation because you see it's leaning to the left. The next one on the right, you can see more positive correlation, R equals to 0.5. And basically, this is now like, with time, you will actually be able to start seeing it for yourself, but calculating your correlation is always very, very useful. So, very well-known correlation coefficient, this Pearson's correlation coefficient. It measures the linear correlation between two variables, and it's suitable for basically variables that are measured quantitatively, all right? This is the definition, covariance, modified by standard deviations of your two random variables. So if you're looking at just a very standard measure to just kind of pull out of your arsenal, this is one that works really, really well. For ordinary variables, though, you're looking at Spearman's correlation or Kendall's tau, and then for nominals, you can use Kramer's D. You'll notice that there are a lot of options out there. And so one of the things that's very useful about using a programming language like Python, for instance, or R, is that a lot of these have already been inbuilt. So they're very nice to use. But I would advise that you truly understand the requirements for each of these different kinds of parameters that you are creating for your correlations. Because at the end of the day, there's a trust involved that you understand well enough that this specific measurement is appropriate for your data set. So if you're looking at Spearman's correlation, Spearman's rank correlation, It's basically a special case of Pearson. It's not really, it's restricted to linear relationships, which is nice, but it measures the monotonic association, so strictly increasing or decreasing, but not mixed, between two variables, and relies on the rank order of the variables. Okay, so rather than comparing the means and the variances, the Spearman's coefficient is looking at the relative order of the values of each variable. And this makes it useful for continuous and discrete, in fact. And you'll notice that the formula is actually very, very similar to that for Pearson. Now, Kendall's tau coefficient, it doesn't take into account the difference between ranks, only directional agreement. So this is actually very much more useful for your discrete kind of data. And this is just the formal coefficient as it's defined. We'll notice that the concordant pairs are basically the pairs in which your ranks can coincide. All right. You'll notice in the afternoon spreadsheet that you'll be doing, there's going to be a lot of engagement with the different kinds of correlation coefficients so that you can understand what to response. Then if you've got a categorical and a categorical variable, to find the relationship between these two, you can use a two-way table. These are very useful as also like a snapshot, kind of similar to a histogram. Basically, it's looking at the count and the count percentage, for instance. So your rows will represent some kind of category of one variable, so whether it's gender, so male, female, and the columns will then represent the categories of the other variable. And then you show the count or the count percentage of these in relation to each other, also understanding the totals around that. And then your stacked column chart. This is more of a visual representation in essence. So you're looking at your two-way table on the left and your bar chart on the right. Like I said, bar charts are everywhere, they're dominating the world. But these are also very useful, just as getting that kind of snapshot. So, and the reason why this is important, I think Glenn is our next presenter after, and he's going to specifically discuss data visualization. And the reason for that is because a lot of the time when people create these reports that go to a manager or go to someone, they just pull bar charts and pie diagram and just throw it on there. But that's not your job actually, because at the end of the day, you know what, Python can do that. It can generate this thing automatically. Your purpose is to be that interface of understanding, to provide the insights, i.e. from this, what we understand is X, Y, Z. That is where you become so important in this whole process. It's not about just creating these plots. Anybody can create them. The point is that you've checked, i.e. the maths and the stats, all of that is correct. And from this, we unearth X, Y, Z. All right. Now, chi-square test. This is used to derive the statistical significance of the relationship between the variables. Test whether the evidence in the sample specifically is strong enough to generalize the relationship for a larger population, which can be extremely useful. It basically returns a probability, and basically based upon this, you can then see if the variables are dependent. And then statistical measures are also used to analyze the power of the relationship. And there are different kinds of methods for that as well. Now, categorical and continuous. When you're looking at this, one of the useful visual tools is a box plot. You basically, for each categorical variable, you're looking at your continuous variable. So if the level, so for instance, you're looking at male, female, you're looking at the specific variables across each of those categories. So if the levels are smaller number, it won't show much of a statistical significance, but then you can actually perform a Z-test, T-test, or a ANOVA. So the Z-test or the T-test, either test assesses whether the mean of the two groups are statistically different from each other. So if the probability of your Z is small, for instance, then the difference of the two averages is more significant. ANOVA basically assesses whether the average of more than two groups is statistically different. So these are very useful also, just in terms of getting an understanding of these two different kinds of variables. Now, multivariate analysis, a bit more tricky. I found that a 3D vector plot can be extremely useful in obtaining a visual understanding of the relationship. So basically, when you're taking two of your features and your target variable, for instance, and then you can actually start to see whether there's a nonlinear relationship depending on the shape of the plot. This afternoon, I'm going to give you guys a research article in which they actually discuss this in detail, which is very useful. And then hierarchical clustering, which leads to a dendrogram. So this is a cluster tree, all right, to represent the data where each group or node links to two more successor groups. And basically they nested within each other, and you can actually literally see how the clusters start getting pulled out as per this graph here. So each node in this cluster tree contains a group of similar data in essence. All right, so the clusters at one level join with the clusters in the next level. So you'll notice that it starts forming these smaller clusters, realizes relationships, and then creates bigger clusters moving upward. So this is also a very useful technique to understand the relationships between your variables. All of these visual aids inbuilt in Python. You just need to know how to implement it properly and make sure that it's the appropriate tool to implement. Now, isolating relationships between features. There are other tools that you can also use to identify specifically, not just if there's a relationship, but like we've discussed, if it's linear or non-linear, all right? So the reason why this can be useful is if you realize that your relationships are in essence linear, the kind of model that you'd use for prediction, for instance, well, maybe linear regression is it. You don't need to go any further than that. It all depends on what you kind of unearthing from this. So here, again, your Pearson's correlation coefficient, Spearman's, Kendall's tau, these are very useful. Your heat map, also, extremely useful tool to get that immediate snapshot of what the relationships are, especially when you've got your input features and your target variables listed there. You can actually then immediately start seeing, these are the kinds of features that my target variable have a strong relationship to. And then it immediately just helps you start to understand what is important within your model structure. Then a joint plot of the target vector and a feature, for instance. This is actually very useful. So it displays the data points according to these two variables, all right? Along with both of the distributions, you see at the top and the bottom. So you can then actually compare these along with your kernel density estimators. And then it actually gives you an optimal fit. You can start also seeing here in your plot, your outlines. Which immediately then starts to show you that there are some points in this relationship that are not functioning as most of the data points are. Now, your nonlinear relationship, this is usually when you start realizing if they're complex nonlinear relationships, that the kind of models or clustering techniques you want to implement are likely to be a bit more sophisticated. Now, entropy is a standard measure of how you can get nonlinear relationships, and there are so many different kinds of options for you in your Python libraries, all right? I'm not even going to list them. I think there's like 20 easily. And basically, depending on what you're looking for, you need to go read, you need to go assess, and then decide, this is the kind of estimator I want to be able to use. So conditional entropy, it's specifically quantifies the amount of information needed to describe the outcome of a random variable, given that the value of another variable is actually an outcome. So here, information is measured in a variety of different ways, but the entropy of y, for instance, conditional on x, that's basically what you're looking at here. And here's your definition. Now, the conditional entropy, if it's equals to 0, that means the value of y is completely determined by the value of x. All right. And conversely, it's basically equals to the conditional entropy of y if and only if they're completely independent. So this is a very quick check for you, just in terms of that kind of nonlinear relationship. Now, mutual information I found is a very useful tool when it comes to understanding a nonlinear relationship. It yields a value from 0 to infinity, which isn't the best. So the higher that value, basically the more information is shared, but it's not really an intuitive measure, unfortunately, but it can be very useful. If you then normalize your mutual information, the normalized mutual information, is basically looking at two different kinds of clusters. So it's basically a score to scale the results. So you're looking at between 0, which is your no mutual information, and then 1, which is perfect correlation. So it's a very good way of determining the quality of your clustering. All right. It's an external measure, which is very useful. And basically, then if you're looking at your different kinds of clusters, it just provides you with a much deeper insight. So one of the articles I'll be giving you this afternoon is an approach that I found in a research article by R. Smith, old article, 2015, where they basically were able to introduce a method to measure the nonlinear dependence between two variables using mutual information to analyze the separate linear and non-linear components of dependence. All right, so it basically gives you an exact value for the proportion of linear dependence, which is very, very useful. So along with your Brock, Dickert, and Shankman test, which then provides you an indication of nonlinearity, it then also you're basically gaining a significant, provides a significance level for the null hypothesis of linearity. So it literally provides you with information on both angles, which for me, in a problem I was considering at the time, where I kind of had a feeling there was a nonlinear relationship, but I couldn't see it visually. So I literally had to like find a method that could unearth this relationship. And it turned out there was a nonlinear relationship between the variables, but it was very small. All right. So the last thing I just want to discuss with you in the last few minutes that I have is feature engineering, where basically you're trying to extract more information from your data. So you're not adding new data, but you're actually making the data you already have more useful. And you're looking at variable transformation or variable and feature creation, all right? And a variety of different ways in which you can do this. So you're basically looking at, initially, as always, understanding your features. Are you looking at categorical features? Are you looking at continuous features? And then your derived features. These are the kinds of ones that you can create from the data, which is then where your feature engineering is coming into play. And these are the three main kinds of features that you're going to have. When it comes to feature engineering, this is very much where domain expertise becomes extremely important, because whatever variable transformation you're conducting, whatever variable creation you're doing, you want to have that check. Within this domain, this makes sense, or you know what, actually you're way off base. None of this makes any sense whatsoever. So things to just remember is that your features must be kept the same during your training, so your experimentation, and then your testing. All right, you can't alter between features and then expect that your testing is an all representative of what has actually happened. So basically the machine learning model needs to be trained on the features represent what it will be used for in the real system. All right, your subject matter experts, they're invaluable here. All right, it's subject matter specialists are in many ways what it is when you're a first year walking up to a professor saying, is this right? And they don't even look at your calculations. They're like, no, that's a subject matter expert. They have such a deep understanding of the context that they can literally just assess there's something wrong, they don't know what, but there's something that's unusual. You need to question whether your features that you're incorporating are useful. And we're actually going to get to this, and then even more so, I think, with Vivian and myself on Friday. You want features that have lots of samples, and you want features that actually contribute. You don't want these random features floating around because they can skew your understanding. And don't fall for perfection. A perfect model that is achieving perfect performance, right? 99%. Actually, usually sometimes if it's above 80%, you need to worry. It tends to mean that you've got feature leakage. So you're probably using information in an inappropriate way, where you kind of, you're testing something, and then you're training on a data set, and then you're testing on it as well, and you're like, oh, it's so good. Obviously it is. The model's specifically been designed for that test data set. So you need to be very, very careful how you're conducting your data. So variable transformation, very useful. For instance, transforming to basically change your distribution or the relationship of a variable can make it much easier for you to engage with your different kinds of features. So you can change the scale of a variable or standardize the variable for better understanding. You can transform complex nonlinear relationships into linear relationships, which are much easier to manage. For instance, with a log transformation, you can reduce skewness. So for instance, if you've got a right skewed distribution, you can take the square or the cube root or logarithm. You can also, variable transformation within the context of implementation is important. So if, for example, you realize that age has an influence on something, for instance, within a specific kind of platform, and you then you can't launch an age-based program. So you can't say, oh, if you're this age, please buy this product, because people might get offended. But you can categorize people in bins and say, if you like from this age to this age, you know, especially for women, apparently they're not supposed to ask our age. I'm not sure why, but apparently it's offensive. So these kinds of strategies understanding your variables and transforming them into a context that allows you for better communication. So standard methods of variable transformation, I'm going to go through them very quickly. You're aware of most of them. Smoothing, so detecting trends in the data where the shape of the trend is unknown. Attributive feature construction, which is one of the things we'll be discussing. Your aggregation operations that can lead to new attributes. Normalization, extremely useful, especially if you're looking at different kinds of ranges for your variables. Discretization. So if you're taking raw numerical values and you're replacing them by discrete or conceptual intervals, this can often help you. And then also concept hierarchy generation for nominal data. So for instance, if you're looking at replacing a numerical value for the attribute age, so if you've got 35 and instead you say middle age, for instance, those kinds of transformations can also be very useful depending on the kind of context that you're looking at. Very simple methods, logarithm, like we've discussed, very useful. Square root, cube root, binning. Binning can be useful, like we said, especially dealing with your outliers. And then feature encoding techniques. And really want to highlight the importance of these. I think it's often underestimated. This is basically where you're converting a categorical variable to numerical vector. One hot encoding is one example, but there are many different kinds of components, and you'll actually be dealing with that in the worksheet this afternoon. This can very much influence the quality of the model that you're creating. And you can't just randomly employ a variable within a context and expect that the machine learning model knows what it's doing. I always say to my first year students that when I taught in MATLAB, that imagine that MATLAB loves you. So the program that you are using loves you. It wants to give you an answer no matter what, which means it's so important that you understand what it is that you're implementing and if you're implementing it correctly. Now, feature or variable creation, there are basically different kinds of techniques. There's where you're creating a derived variable. So you're creating a new variable from existing information. So for instance, if you're taking the log of a variables, binning, averages, all of those different kinds of things. And then your dummy variables. This is one of the most common applications of a dummy variable is to convert your categorical to numerical, like we said with one hot encoding. And this is extremely important. Often it can increase your data set quite astronomically, but very important component. Now, feature selection is something that, like I said, on Friday, we will be discussing in much more detail. So basically what you want to be able to do is, when you've got your huge data set, you want to be able to say, these features, these are the ones that matter, all right? So you want to basically be able to say, like, when I use this feature, it's increasing the quality of my model. It's increasing the predictive quality of my model, all right? So basically, if you use this feature, better prediction, or guess what? If I remove this feature, it makes no difference. That kind of understanding, you want to be able to put in a structured format. So you basically want to discover those top critical features and then remove all the non-essential data, because that's literally just wasting your time and probably providing you with an incorrect understanding. So you basically are able to allocate these feature important scores to each feature, and we will discuss with you how this is done. We have a variety of different ways in which this can be done. So in many ways, while this feature selection is seen as part of your feature engineering for your employee regression or classification techniques, you're actually using unsupervised learning techniques. It's also called dimensionality reduction. So if you're thinking of PCA, for instance, those are all the different kinds of techniques that you can use here. So I've listed here just a few possible measures and their associated models. So if you're looking at gene importance, your PCA, like I measured here, also allows you to consider. And this is in essence how you'll be able to then isolate, okay, these features matter and the rest of them don't. So this is the exploratory data analysis notebook that all of you will be receiving from me with a data set via email this afternoon. So please check your emails. And yeah, thank you very much for listening. I hope it was at least a little bit useful. Right, we probably have less than a minute. And our next speaker is already online. Len, are you with us?
Hi there, good morning. Yes, I'm here. Lovely to be here.
How's it going?
All good, thank you very much. How about yourself?
No. It's very cloudy. this morning, so I'm happy. Do you want to start sharing your screen, Len?
I'll do so just now. Thank you very much.
Okay, so while Len is organizing his screen, let me maybe just introduce him. So Len Marais is the head of, I think he's now moved to another country and might have taken up a completely new position. So Len, please correct me after this. Was the head of Currency Integration Division and Currency Management Department in South African Reserve Bank. His main focus, which is why I begged him to be here today, and he luckily said yes, I'm sure to his eternal detriment, is specifically to provide you with a context of how data visualization can either be extremely useful or completely pointless, where it can also just, in essence, provide you with understanding that's completely erroneous. And this is where, as people that are conducting data analysis, data visualization, you need to be very aware of the story that you are telling. What are you communicating to your audience when you are doing data visualization? So Len, are you ready to wow us with your presentation, please?
Well, I'm not sure about wow, but I'm ready to take you through it, right? So that should be good. I'm going to switch on my camera. Please let me know if at any stage there's issues with actually hearing me, or if there's some problems, then I can switch that off. Can you at least see my screen?
Yes, we can. We can hear you perfectly as well. Thanks.
Fantastic. Thanks so much. So good morning. As mentioned, my name is Len. Please feel free. This is a conversation. I've got a few slides which I'd like to talk you through. Feel free to interject, to interrupt, and to let's have a conversation. All right. So I had a look at this topic, and then I had a look at my experience to date. And this is very much my career over the last 20 odd years. This is very much what I've been doing. Now, for those astute members of the audience, which I have no doubt all of you are, you'll very, very quickly pick up that nowhere in there did I mention infectious diseases, barely mentioning modeling, no mention of mathematics, and definitely no mention of machine learning. I think to make us even worse, I'm not a professor, and I know in an academic environment you might be shocked, but I don't even have a PhD. All right, so you really mixing with the lower echelons of society here. So apologies in that regard. I did note that I am, in the entire agenda today, I'm the only individual that's a Mr., not a professor or a doctor, but I still thank you for your time, and hopefully I can actually share one or two key tidbits with you, which would be of use in your journey. And the main reason for that is my career to date has very much been focused on decision making. And all of those decisions are very much focused on issues with long-term and material impact. And that's whether that is decisions or strategic planning and positioning for organization as to where that company should be within 10, 15 years, making decisions, as mentioned, at the South African Reserve Bank, where we focus to say, well, what does currency look like in 10, 15 years? What does physical currency
Len, can you hear me? Len? Len is weer terug met ons. You with us? Yes, commute.
Apologies. Sorry, that was the important part, and now I lost you. Apologies for that. Let's try that again.
Thanks.
There we go. Sorry about that. So I'm not sure where I lost you. Let me hop in here. The key point is, I think, with regards to decision making, these long-term decisions that have very real and material impact, real budgets, real lives, structuring organizations, you always work under a lot of uncertainty. And I think that's the key part. The data sets which we typically have access to Quite often it's incomplete. A lot of the data is irrelevant. Quite often it's actually incorrect, right? And it takes you a while to actually work through that and find that. In addition to that, if I consider this audience, your depth of knowledge is extensive. Quite often, and most typically, that is not the knowledge base of individuals in industry that you might engage with. And whether that is from a stakeholder that's supposed to provide you with something, or whether that is your end client to which you actually need to provide a data product. So most individuals that I've had the pleasure of working with, they're either uncomfortable, unable to work with data, or quite often unwilling. There's really is a significant amount of unwillingness and concern with regards to actually conveying messages. And it's for that purpose that data visualization and the manner whereby we convey the information which we have actually, or the solutions which we have crafted, becomes critically important to do so in a manner which actually suits the need of that end client. So I think a more appropriate descriptive for today's conversation would have been data acquisition, analysis, and visualization. I'll touch on the visualization towards the end. And I really want to talk about a cautionary tale of context. And I think that is something which, in my number of years working in industry, that's the key message which I've really come to appreciate, to understand, well, whether that is obtaining information or sharing that information, if you cannot provide that context, the solution, whether it might be correct to the third decimal or not, carries very, very little weight. So that's what I'd like to focus on. So if we jump into data acquisition, this is an old example. I'm not sure the average age of the audience today. This dates back to 1989. So apologies. I'm happy if some of you actually recognize this. This actually pertains to the Mars Climate Orbiter. So this was a probe which was launched to actually orbit around Mars, actually do atmospheric readings. It was supposed to be a relay station for a subsequent mission to actually drop a probe on the surface of Mars. Launched in December 1989, and around 10 months later, as it actually approached the surface of Mars, it actually burnt up in the atmosphere, and they actually had to pull back, assumed computer code errors, assumed a communication error, and as they actually rolled back and actually started to decompiling all of the codes and all of the hardware that actually was embedded, they learned that between the JPL team as well as the Lockheed Martin team, the one team had used the matrix system and the other had used the imperial system. Now, as simple as that might seem, and as simple an error as that might seem, if you consider for a moment that this is the top teams at NASA, and this is the kind of mistakes that do slip in, it's quite feasible. The rest of us in our engagements on a day-to-day basis might similarly be subjective to this kind of error. Hopefully the implications are not as severe as those experienced. In this particular instance, they had a particular numeric value. They referred to it as a force. The one team assumed that there is pounds of force, and the other team assumed that it was newtons per square meter. And if you do not pause and have those conversations and ask those very stupid questions around what exactly do you mean by, quite often these kinds of mistakes can creep in. This is something which, to this day, on a day-by-day basis, I actually experience. If you talk to a commercial entity, as an example, if you talk to you have a particular value, and let's say we refer to it as sales, finance most probably refers to that as the value of goods sold. That's what they consider a sale is. IT might say, well, number of transactions or number of transactions per hour processed on their equipment. Manufacturing, they would focus on the number of units sold. And logistics, quite often, when they talk about sales, they might talk about weight, which has actually been shipped or distributed. So it's of critical importance when actually acquiring any sets of data to really interrogate and ask those questions to say, well, what is implied with? And as much as you might feel that those questions are irrelevant, quite often, whoever asks that question, it's much appreciated by a number of people attending a session, because quite often, a few of us don't actually know what was implied. In your particular area of expertise, focus on this particular topic, I would ask those simple questions. If we talk about a patient, what does a patient actually imply? Is that somebody that arrives at a door? Is that somebody that's already been presenting symptoms? Is that somebody that's being assessed and tested for a particular pathogen or disease? Or is it somebody that might be diagnosed? if you consider a study on the efficacy of a particular medicine, I would imagine that a patient is somebody that has already been diagnosed and is experiencing some form of treatment. However, if you are a hospital administrator and you're concerned about availability of beds, your patient is somebody that has actually arrived at the door. And it's in these very simple descriptors where things can go wrong very, very quickly. And it's again, from my side, a cautionary tale. Please do keep these things in mind. The number one frustration which anybody that moves into industry experiences with regards to working with data, building phenomenal models, building beautiful visualizations, is data. All right, getting that data, acquiring and getting it in a usable state. 80% of time and effort will be spent on actually cleaning or obtaining that data, which sounds exceptionally frustrating, but the reality is, and I'm putting numbers to it, I'm going to say the overall majority of the success thereof very much similarly also depends on the usability of that data. So time spent on really understanding data is time well spent. It will serve you well in the longer term. Forgive my X-Files reference here, but when it comes to data and actually getting data, I've never been at a client where day one, they do not promise you that they have all the available data, it's clean and it's ready to be used. I have never experienced that, not in a single instance. So when it comes to data, I always say trust no one. Believe me, it's very rare that the data is actually available in a usable state. And that could very much be that data sourced from different systems. Now, whether that system is a software solution or whether that's actually a method of acquiring data, quite often people that go into the field to obtain data, the result, even though you've given them exactly the same instruction, the result is actually captured and reflected in a very different manner. Quite often what one sees is a system upgrade or change. I cannot tell you the amount of times where up to December 2019, the data looked a particular way, and then thereafter it looked either fundamentally different, which is fine, because then at least you know where the problem is. Quite often, it implies there's a column shift or two columns have changed over. And if you don't actually spend the time to really understand that, you find very odd and very strange results in your final data visualizations. Any process upgrade or change, if you consider, say, microbial scanning technology, quite often, the third decimal on one set of equipment gets dropped, and on a different set of equipment, the third decimal gets rounded. As an example, all of a sudden you change equipment and then you see a change in your results. If you are not aware that the equipment has actually been changed, you actually pick that up as a positive or a negative trend in that regard. But then, of course, locations and geographies, things work different in different environments. Again, as mentioned, feel free to ask those questions. And then finally, kind of encapsulating all of those, the question would be, who captured the data? Is this a medical professional that actually did specific lab-based testing and experimentation, or is it actually a general practitioner who happened to actually encounter something, capture it, and actually share that in some kind of meta-analysis? If you understand who captured it and what it was actually captured for, it fundamentally shifts the manner in which that data actually reveals the reality behind the process underneath it. So that's very much from a data acquisition perspective. Key message, context is key. Take the time to really understand how this data was obtained, what was the intention behind it, and how do we know we can actually trust it, and what does each one of those variables in there actually describe. Similarly, if we then take that next step with regards to data analysis, now if we take this very simple, and I'm going to use one or two oversimplified examples, this is the domain where people with advanced mathematics and computational ability, this is where they want to play. You've got a few data points, and you are actually asked to make a forecast for some point far off into the future. Now, if we consider this particular I don't even want to say data plot, but it's got a very limited data points. And we say, well, let's take it out a few thousand points into the future. What exactly could that be? Each one of you with very high levels of accuracy, with very strong arguments, with very strong numeric abilities, I have no doubt will create a different projection for each one of these, for these points or for this particular trend line. The reality is, if you do not understand what exactly we are looking at, right? And in this instance, this is based, say, on my height, where I tape it out at the early 20s, and over time, it's actually remained the same in future. It's actually going to take time. If you don't have that required context, then it's very easy to actually consider that top view, assume it's Bitcoin and say buy. Whereas in the reality is that if you have that additional context, you can actually pick up to say, well, this might not be something which exhibits the growth pattern which I had expected. Now, this is an overly simplified example, and of course, none of us will make this this mistake, right? Except sometimes we do, right? If we consider, for those of you not familiar, the picture on the top reveals a soccer ball. The picture at the bottom references a linesman at a soccer game. And through the course of 2020, a set of camera equipment, which was supposed to track the ball throughout most of the game, actually incorrectly picked up on the referee's bald head and actually tracked that bald head as it moved around on the soccer pitch. Now, I'm not sure whether, it depends on how big a soccer fan you are, football fan you are, whether you would consider that to be as big a catastrophe as the Mars Polar Explorer. But the point being, these are simple issues which do pop up and which do occur. And it's only until you've really asked that question, provided or queried the context to say this ball is only moving along the outer perimeter of a particular perimeter before you could actually determine that there might potentially be an error in your estimation or your forecast. Similarly, if we consider data analysis, this is something it was briefly touched on in the previous presentation as well. We talk about averages. An average, for those of you who are deep into data science and statistics, really have a very different grasp of what an average is versus the average not the average, versus the layperson out there. And very few people realize that the shape of a particular distribution significantly yields sort of different implications. Although a single point value, such as an average in this case, and this might not be the best example, although an average might be consistent or comparable, and for these bottom graphs, it would depend on the size of the spike and the length of the tail, but all of these could yield a similar average. So whereas the underlying model, which actually tries to explain the behavior out there, actually implies fundamentally different behavior. But if we focus on a single point value, then quite often a lot of the nuance and the subtlety is actually lost, and the true value, unfortunately, in that process is lost. And we see this often. This was, I quickly Googled an excerpt. This is from, well, exactly a month ago. What is the average worker gets paid in South Africa right now? So a lot would depend on what that curve looks like, right? And very important decisions around labor reform and around executive remuneration is made based on these kinds of point values. Whereas if you better understand the curve that underpins it, it might give you a very different view. Similarly, and this is from the US, it's also through the course of last year, this is again a topic of much consideration. Wage gap on average. My point is not to try and disprove either one of these statements. I think exactly the opposite. It is actually to say these kinds of topics are very complex and it's multi-layered and it's actually got a lot of nuance. And when analyzing any data set, when presenting back any kind of information, try to avoid that single point value. Quite often from a statistical perspective, individuals include additional descriptors. The typical data client quite often does not understand that. So try to do that, and that's where we're working towards data visualization in a manner which is truly acceptable and understandable without having to have a deep understanding of any form of analytics or statistics. Touching on average just as an example, with regards to the context of what you're trying to achieve here, we talk about recovery rates, infection rates, incubation periods, all of those imply an average. As important as that value might be, as I mentioned, consider the curve underpinning it and what is that second layer of analysis or understanding which you can actually share with the end user client in order to help them really understand the purpose or the outcome of a particular study or a piece of work which you might have done. So I'm not sure who's familiar with spurious correlations. This is, again, one of my favorite websites. This is a view on the per capita cheese consumption and then the number of people who died by becoming tangled in their bed sheets. This is real data. It's verifiable. And this particular one is correlated to close to 95%. All right. Similarly, if we have a look at the consumption of mozzarella cheese versus civil engineering doctorates awarded, this is correlated by close to 96%. All right, so there's obviously something here. The typical layperson in the majority of the engagements, this is the kind of thing which we read about in a newspaper on a day-to-day basis. This would be sort of put forward as evidence, and it really requires that next level of interrogation to understand what exactly this is, what this is implying. Similarly, and not wanting to focus only on cheese, if we look at margarine, the divorce rate in Maine is 99% correlated to the per capita consumption of margarine. So I think to all of you, you are well versed in these concepts, correlation versus causality. Majority of people, those individuals who might actually consume your data products, your final end products, they most probably are not. And as much as you can try to explain that in the deepest of statistical terms, the reality is people who look at this curve say, I hear what you're saying, but something's obviously happening. So really spend that time and focus and attention to try to analyze and actually present final results in a manner which makes the most sense. Quite often, these are terms which we see. This is a positive correlation between the amount of chocolate consumed and Nobel Prize winners within a particular geography. This is a real scientific study. Go read it. Interesting conclusions. Similarly, potential association between antibiotic exposure and then weight gain in early childhood. BMI seems to be associated with increased risk of several cancers. Again, a lot of these are headlines which we might see in newspapers or in magazines on a daily or weekly basis. These are actually scientific studies, and quite often the true driver behind this is glossed over because, well, these two lines obviously do match. Something is happening, and it's quite often it's missed by those who do not truly interrogate the outcome. And we can pause and actually provide that context. And I think that's the key message I want to drive to. You are unable to actually provide that additional context. So please take your time to do so. Quite often, analysis can and does yield those beautiful moments when it yields counterintuitive answers. You build a model, you get an answer which you don't expect. Those are very refreshing moments, and it's always very rewarding. However, quite often, those counterintuitive answers might mean that it's actually an indicator of a highly predictive error, right? So quite often, if it's too surprising, if it's too beautiful, quite often it's wrong. So take that time to really pause and say, well, what was the context? Did I really get it right when working through a particular model? Those of you who have different experience with machine learning, let's be honest, and many people out there might not agree, we can get a model to tell us pretty much anything that we want, right? So just keep that in mind as you work through your particular models and ensure that we don't actually get caught up ourselves by those moments of brilliance when we are refreshed and surprised. We touched on correlation versus causation. Again, nobody on this forum would ever get tripped up with that, except we do, right? So just keep that in mind as you move forward. And then many complex systems, and whether that's a system or a biological system or a large entity, there's multitude of interdependencies and interactions, and these things are complex, right? Take your time to actually embrace and understand those nuances. Don't distill it down to a single point value. As much as that is, we all get asked for that 10 or 30-second elevator pitch to say, well, what should we or what should we not? The reality is some things are complex, some things are nuanced, and some things require a pause and a longer and a detailed, more detailed conversation. Again, if I haven't mentioned this before, context is key. Finally, touching on data visualization, which is very much sort of in this simplified view, the pinnacle of where we're trying to get to. I've used maybe the worst data set ever to actually try to illustrate this point. I think what I've taken is literally Googling the Rand US dollar exchange rate and some of the things which we quickly picked up. It touches on the volatility, how the Rand's actually moving, quite often words such as pile up, which have negative connotations to them. If we consider, and this is the last month or so of ZAR to US dollars fluctuations, then you can see, yep, there's obviously that fluctuation, that volatility, which is mentioned, is obviously very apparent. The manner in which you actually present that data, this is the same data set, matters, right? So all we've done in this particular instance is down the left-hand side, we've just changed the scale. Now, again, to all of you on this call, I have no doubt you would have picked this up in an instant. Quite often, if I show the bottom view, I would actually say, well, it's very stable, slight sort of a periodic harmony in it, but it's a very stable. Whereas one shows the top view and it seems erratic. And if you consider guys who do currency trading, they actually take this. This is on a day basis. They take it down to the minute or second level. And as you can imagine, that it gets completely erratic, and they make these decisions on it from 1 second to the next on this notion of volatility and actually capturing those key moments. But the manner in which you actually share that data very much determines how a typical layperson might potentially experience it. You can either talk from, this was sort of from the beginning of this month to about a week or so ago, there's a 5% drop, right? Or you could say, well, there was a 75% change. So to most people out there, and I'm using this purely as an illustrative example, these messages are received in a very, very different manner. Similarly, we just spoke about the perils of an average. We could take that exact same view and you can say, well, we're only 1.7% down from the monthly average or the rolling average or the X month average. That's another way in which we can either take a particular data set and actually portray it as being better or worse. Purposely didn't include a view on the South African economy and socio-economic state, which was presented in a very reputable newspaper about 2-3 months ago. And it had, I think, about 12 to 15 different visualizations, which were portraying a very specific view. And many of these things around adjusting of scales or determining starting points were actually included there. And it was accepted as fact. And for most of us, picking up a newspaper, especially if there's a preconceived bias, it speaks to that bias and it actually just reinforces that incorrect view of what might actually be happening. Similarly, you might say, well, there was a 0.28% uptick on the final day of trading, or there's a 0.72% growth in the final week of trading. All of these are correct. Depends on what the message is that I want to actually convey. All right, so it's all off the same data set. Another I don't want to say trick, but it's almost a trick which is quite often used is, what do you actually utilize as your base for reference? You would see exchange rates, you see this, the price of gold, you'd see this, the price of Brent oil, you'd see this. Quite often there's a point in time which is used as the reference point. And what I've just taken here is 2 days apart. The one is the December 27, the other is December 29, so literally 2 days apart, and referencing the percentage shifts on each subsequent day back to that particular point. For anybody who is not interested in the details, which most people who consume data aren't, these two graphs at a very quick glance reveal a very, very different message, and it creates a very different impression. Yet, neither of these is incorrect. It's literally just using a 2-day shift on the base. Stepping a bit further to talk about sort of the more graphic rich data visualizations, and this comes from a website, Information is Beautiful. They've brought out a book about 2 years ago around data visualization. It's well worth anybody's time who's actually interested in this. So this is the kind of thing, again, colors, same scale, which is phenomenal, which is a rarity. Quite often when people compare different data sets, they actually use different scales. That's something which you'll pick up as well. Same date ranges at the bottom, so this is comparable in that regard. However, this touches on COVID and unfortunately COVID deaths in this instance. It depends on the user of this data. My view, to do a country-to-country comparison, I would say if it's not on a per capita basis, it serves very little purpose. The population of the US is 5 times more than the population of South Africa. So what does this really tell us? So again, that's an example. This company creates beautiful data visualizations, but this depends on what the end user need might be. There might be subtle differences between what is actually required. Stepping a bit forward and moving away from more sort of traditional visualizations, on the left-hand side, well, it's fairly sort of incubation periods for different comparative kind of infectious and diseases. On the right-hand side, that's a view which, again, it's very nice, very intuitive to understand. Along the vertical axes, the amount of individuals that pass away who actually have contracted a particular ailment. and on the right-hand side, the infectiousness rate, or the amount of individuals to whom you've actually transferred. And very quickly, you can get an intuitive view to say, well, chickenpox, all the way at the bottom here, highly infectious, right? And I think all of us who've lived through primary school will sort of can account for that. But fortunately, it's not a lot of people that pass away from it. Whereas if we actually considered MERS or Ebola also not as contagious as one fortunately might fear, but excepting 50% rate of individuals actually contracted passed away. Very nice view, again, contextualizing COVID. As much as we spoke through it right now, this is the kind of view which you can put in front of a lot of people, and intuitively they can actually understand it. But it can and does get better. I've stayed with a few coronavirus and COVID-related items. So what they've shown here, literally different kinds of activities from low, medium to high risk. And as you can see, overlaid on top of that, the actual size indicates not only the position on the axis, but also the size indicates the inherent risk. And then they've also done a color scale from light yellow to dark red, which reads very easily and very intuitively. The majority of people that view this would very quickly understand what is actually being explained in this particular visualization. Something similar, again, this is actually potential treatments for COVID, and I'm well aware of the time. I'm just about to wrap up. Consider the all the way from those items which were based on the study considered to be potentially harmful, and I'm not going to debate or discuss any of those. This was based on this particular study, versus all the way those treatments which were considered promising or good. And interestingly, what they've done is the size of the actual circles that they've included here is the amount of media attention. So that's something which I find very interesting for those things which are more conservative, conventional, versus those things which are a bit more alternative. And actually, you can see a clear distinction how those receive far more attention in the media. Again, this visualization, I might have changed the color scale. I would have potentially made those things which are harmful, say a dark red, and all the way to those things which are promising and good, maybe a green. Again, just to make it simpler, there is an inherent view amongst all of us that green means better and red means worse. And this steps one step further, and it actually moves away from traditional visualization. It actually moves towards infographics. And this is, again, a very powerful method. And all this particular view shows is these are some of the items which are developed or grown or produced across the globe. And this is where they're actually consumed. And those lines give you a sense of the proportion. These bottom dots give you a percentage per capita. Again, very intuitive, easy to understand. And very quickly, you can pick up which different geography consumes what without having to explain it to anybody. My favorite, and I'm gonna end off with this one, is if you ask the question, what is the ultimate dog, right? And you know, this again, anybody who's a dog lover, this would be a bone of contention. But just consider the amount of information which is actually included in this particular visualization. And I'm not saying use this. I'm just saying this is a phenomenal example. Along the horizontal axis, this is some kind of data score. So they've done some kind of assessment, and that's actually plotted on that horizontal score. Then similarly, there's a popularity from least to most on the vertical axis. And look at the additional detail which is actually included. So they actually, if a dog leans towards the left, it's considered unintelligent. And if it's actually leaning to the right, it's clever. So I'm not sure. Have a look at your dog of preference, and you'll quickly see where it sits there. Similarly, sizing has been included for the size of the actual canine, and then the color, that's an additional layer, is actually the kind of dog. And based on that, they've done this particular mapping to give a sense as to a particular scoring. I like this because it has so much information, and again, as irrelevant as the outcome might be, it's a great example of what one can actually do. So key points: design with the end user in mind. Data should always be intuitive. If you have to explain it, you've gone wrong. Think of what those key messages are and focus the visualization around it. And as far as possible, ensure that it's done in an open and objective manner. Do not manipulate the visualization. You might get away with it once or twice, but it significantly sort of discredits the value of the work that you had been doing up to that particular point. If I haven't mentioned it before, when it comes to visualization, context is key. I'm going to end off with this. We're all familiar with the Dunning-Kruger effect. I think all I want to leave that with you is to say, careful where you find yourself on the curve. I think we've all been in that example, in that state where we feel we know more than those around us. Those of you who work with data, you will be enabled and equipped to actually provide significant insight to others. And quite often, it feels as though you need to drag people along. But just be careful and don't let hubris take over, because you will be wrong from time to time. We all are wrong from time to time, and make sure that at least you're at a point on that curve where you can admit it and correct it and move forward. And that's it from my side. Thank you very much.
If you didn't hear it, there was tapping in the room. So thanks very much.
Very kind of you. Thank you so much. Thank you for your time. Much appreciated. And thank you for the opportunity.
Really appreciate it. I hope that was useful to everybody in the room and everybody online, just getting an understanding of how important it is that you really take the time to choose your visualization tools properly. It can really make all the difference. So for those of you online, we are on this side just going to have a quick cup of coffee and a snack, and then we will be starting again at 11 o'clock. Our next speaker is Dr. Messiah, and she will actually be talking to us about dynamical systems and topological data analysis. So we will see you all soon. Thanks.
everyone. Thank you again for joining us in this workshop, everyone online and everyone here in person. We appreciate it. So my talk for today will be on two topics, but I'll try to connect what topics, what I discuss in dynamical systems to this recently emerging field in applied mathematics, which is topological data analysis. Okay? So just quickly, what is a dynamical system? It is it consists of two important ingredients: the space, the state space, and the phase space, and the rule F that acts on points of X, okay, and tells us how this point evolves in time. Okay, so depending on what time capital T is, if it's continuous or if it's from a continuous or a discrete space, then your dynamical system is either continuous or discrete. If it's continuous, it's called a differential equation. If it's continuous, it's called differential equation. If it's discrete, it's called a difference equation. Okay. All right. So these are just this is just a table that summarize what I mentioned a while ago. Okay. So usually, well, for me, I work with discrete time systems, but I know that most of you, especially the students here in working on infectious disease and mathematical biology, use a lot of continuous dynamical systems. Okay? So we usually call it a map if it's a discrete dynamical system. If it's continuous, you call it the flow. The F is called the flow. Right? So regardless of what dynamical system you use, okay, it's almost always interesting to consider the deterministic case. Okay? Otherwise, for the non-deterministic case, you have multiple outcomes for each input. Right. All right. So dynamical systems is used quite a lot in infectious disease modeling. Okay. What we're familiar with, especially these times, are a lot of models, say SIR model, SEIR model. S is for the susceptible, I for infectious, and removed or recovered individuals. Okay? So what everyone is probably familiar with is the dynamical systems approach in approaching this type of problems. There's a statistical approach, there's mechanics approach. Okay, but for the dynamical systems approach, okay, the most popular or probably simplest model is the compartmental models. Okay, on Wednesday, there's a lot of specialists in infectious diseases and modeling that will talk, okay, on Wednesday. So I'll just give an overview, but more details of this will be discussed on Wednesday. Okay, so for a compartmental model, you have those these blocks, those compartments where you have individuals, whether they're S, in I, or in R. And aside from the compartments, there's also processes involved between these compartments. Okay, the processes either increase or reduce the numbers in each compartment. Okay, so these are just the terms that are used. You may be using other terms, but usually these processes are either called inflows and outflows, and they have signs corresponding to them whenever you want to construct a model. Okay, so although SIR model is basic or simple, as I mentioned, it still has the hallmark of complex systems. Okay, so in dynamical systems, you can go to the very interesting part of it in the chaos theory or complex systems or ergodic theory. So complex systems can be talked about when you discuss infectious disease models. Okay, so it's complex just because there's really interaction between individuals in compartments. Okay, all right. So this is, sorry, it's just a small equation, but what we usually do is, once you have your compartments, your figures, right, the representation of the graphical representation of your model, you then construct your equations. Okay, and usually these are a set of ODEs. Okay, and if you want to implement that, implement it on a computer, and everything should follow. Okay, so because I'm under visualization, this topic is under visualization. So I'm just presenting what we usually deal with dynamical systems in infectious disease. But what I really want to discuss today is visualization of time series. Okay, so the setting is the following. Okay, once you observe a time series, what's really happening is that it's coming from some unknown function, dynamical system, okay? Some possibly unknown set as well, M, but for results to be nice, you probably want your set M to be at least bounded or finite dimensional compact manifold. Okay, all right. So what's happening above here, this unknown system, is that there is some sequence of, iterates, okay, under F that happen. F is unknown, M probably at least, bounded. Okay, but what's happening up there is those X of X. Okay, but what you're observing are the U's of X. And these observations are related to what's happening up there, the X of N's, by some continuous function U, okay? Okay, and the relation is the following. Okay, each observation that you see U sub n is related to X sub n, okay, by the following. U of n is the image of that continuous function raw, okay, and X of n is related to F by this equation. Okay, so that's the setting. You're observing something, but you don't know where it's coming from. Okay, all right. So this is just what I mentioned a while ago. Okay, this is what we have, and this is what we know. Okay, and sometimes, any small assumption that you think of, okay, on U sub n or even those F's or M, okay, can say something about the underlying function, usually unknown. Okay. All right, so this is one approach if you want to study time series using topology or topological approach in time series. It's called time delay embedding. Okay, so what you do with the time series, because we say time series is just a sequence of numbers. Okay, so what you want is to convert that sequence, because if you plot it against T, it's just, it's nothing interesting. Okay, so what you want is to basically extract any underlying feature of your time series, and this is done using time delay embedding. Okay, it's essentially constructing vectors out of the time series depending on specified parameters. Okay, right. So the parameters needed for time delay embedding are the following: the tau, the time delay, the window size, which is d minus 1 times tau, okay, and the stride, which is just the difference between the t's, the successive t's, which is usually the same for all i's. Okay, so what it does is the following: it takes a element from your set, the time series, okay, and from each of that you construct a d-dimensional vector, or vector of size d. Okay, right. And what happens is that if your time series has a periodic structure, then that's going to reflect in the reconstruction or the embedding. If it's non-trivial, then it's also going to reflect in the embedding. Okay, all right. So how does reconstruction work? Okay, so it's just taking, depending on what the parameters are. Okay, so these are the same assumptions. Depending on what the parameters are, you construct a sequence of m-dimensional vectors, or I used it a while ago, but here it's m-dimensional vectors from your time series and plot those set of points. Okay, so whatever you're observing, okay, which is probably this, the collection of what you're observing is probably something interesting or not. Okay, but essentially the reconstruction, the constructed space, okay, from your observation using time delay is A sub m. Okay, all right. So this is a famous theorem in dynamical systems when you want to work on time series. It's Tatkin's embedding theorem. Okay, so what Tatkin's embedding theorem states is that with the correct choice of embedding dimension, okay, whatever you reconstruct, okay, using time delay, okay, will be homeomorphic to the underlying space. Okay, right. But the problem here is that for Tatkin's, if you reconstruct in a dimension n, okay, it should be something that's greater than or equal to 2 times the dimension of the underlying manifold plus 1. Okay, so this is really something that was a breakthrough during his time. Tatkin's even passed away just recently. Okay. Yes, so that's the problem. The problem here is that you have to know the dimension of the underlying manifold, okay, which sometimes is not, more often than not, is not available. Okay. Right. And by embedding, it just means it's an injective and structure preserving map. Okay. So this is an example, and the popular map again in dynamical systems, the N1 map. Okay. So it usually looks like a boomerang, okay, sideways. Okay. But in this case, what we're doing is we're reconstructing the set. Of course, we already know how the N1 map looks like because there's a explicit equation. Okay, so what we're doing is we're testing several values of the raw. Remember, we want the raw, the continuous function, which we specify. So we're testing various functions of raw, either it's x plus y, or x minus y. Okay, and verifying whether it's close enough to the real structure of the N1 map. Okay, so for the N1 map, it looks like a boomerang. It's like this, the first figure, but sideways. Okay, and note that this one is the famous N1 attractor. Okay. It only appears for the classical parameters A equals 1.4 and B equals 0.3. Okay, so if A and B are not chosen as those, then you're not going to get that nice figure. Okay, all right, and this is another reconstruction. On the left is the time series. Okay, first is the periodic one, and the other one is not really periodic, but it's recurrent. Okay, so if we reconstruct, say, A, okay, for those parameters, T equals 3, tau equals 8, and stride equals 10, okay, that's how the time series looks like in D equals 3. Okay, same thing with the second time series. Okay, so it looks periodic, but actually, if you reconstruct it, if you do time delay embedding, there's no this is a word, ellipticity. Okay, so it's a general result. If your time series is periodic, then if you embed it in any dimension, okay, proper dimension, then there will be ellipticity, okay, that appears. Okay, and this one is a very nice site, the Giotto AI. It's a GitHub site where I usually play around with lots of notebooks. I use it in a dynamical systems class, especially for time series analysis. But this is also for topological data analysis, which you'll see later on. Okay, there's lots of notebooks that you can play around if you have a data set that you are interested on. All right. Okay, so this is just the thing that I want to point out regarding embedding using Takens theorem. And the problem really is the dimension D. Okay, so if you don't have that, what next? Okay, you can play around with different dimensions, but after that, okay, there must be other things that we have to think about to solve that problem of unknown D, capital D. Okay, so I didn't write the formula here, okay, but there are two techniques to determine the reconstruction parameters. Okay. The first is the average mutual information. Okay, Prof. Hardy talked about mutual information a while ago. Okay, for this one, it's just the first local minimum where the AMI occurs. Okay, and the four false nearest neighbors technique is used to determine the dimension D. False nearest neighbors is sometimes if you choose a small d, then there's going to be chance that the trajectories cross. Okay, so what you want is, no crossing of trajectories and the correct dimension so that false neighbors disappear. Okay, all right. So this is just one application of state space reconstruction in infectious diseases. Okay, it's called CCM, convergent cross mapping, and this is from Sugihara and T. Okay, so usually what we want in most of the sciences, what you want when you have lots of variables is the cause and effect, the causation between variables. Okay, so it's important in many scientific fields. Okay, and what does it do? The CCM is a model-free method, okay, but it uses state space reconstruction, okay, to infer causal interactions. Okay, and usually what you just need are really time series, okay, a set of time series, and then do reconstruction, and then apply, of course, some more techniques, but at least reconstruction is there. Okay, and get results on causality, okay, between variables or between sets. Okay, all right. So this is a paper by Kobe and Baskerville. Okay, they studied I think six infections. Okay, mumps, polio, and 4 others, remember, but we'll see in a bit. Okay, they studied 6 childhood infections in New York and Chicago, pre-vaccine era. So this is about 1900s to 1950. Okay, so they used CCM to test causality between from Y to X or X to Y. Okay, and these are the steps. Okay, so they have bootstrapping between the reconstructed X, a reconstructed point in Y, okay, and Y hat, Y which is Y hat, and then test Y and Y hat, which I'll show the figure a while ago. They also have 2 criteria. Criteria 1 is cross map, and the other one is negative cross map flags. Okay, so in this case, they play around with the L, okay, to get the best L that works for your time series, for the 2 time series. So this is the procedure. Okay. So you have your X here, you have the 2 time series that you want to analyze, and it goes through this procedure. Okay, so X or 1 time series is reconstructed, it's computed, it's compared to the reconstruction of another time series, okay, and it constructs this correlation distribution, okay, and tests these 2 criterions, criterion 1 and criterion 2. Okay, so what's nice about this paper is that everything is available. The codes, the notebooks, the data, they're all available. So that's really what I like when I'm reading articles. I want to play with the the codes, and the thing is I want to use the method, okay, and it really helps if you have the codes. Okay, so this paper has the codes, everything, okay, and this is the result. Okay, so in this case, they're only using criterion 2, okay, and this is what they have. There's either they use 2 methods: delay embedding or time delay embedding methods, using univariate correlation or random projection method. But in any case, you see a causality between, these diseases in New York, which is green, and in Chicago, which is red. Okay, so these are the 6 diseases: polio, mumps, measles, and so on. Okay, so take note, there's no modeling involved here. You only have your time series, you do reconstruction and apply their method. All right. Okay, so that's basically one way of using dynamical systems in time series analysis without using models, but visualization. Okay, so the visual results that you get are used in some techniques here. Okay. So another method of visualizing time series is this technique, or the field. It's a recent field. It's a TDA, topological data analysis. Okay, so what it does is really uses tools from topology, even computer science, okay, to understand data. Okay, so its main idea is to impose shape on data, okay, because for its mantra, data shape has meaning, and meaning has value. Okay, so the underlying theory for TDA is really, the pure math. Okay, but once you understand that, you also have to learn, the computational side. Okay, so the TDA method was, the pioneers for TDA are the following: the Stanford group, the Rutgers group. Stanford group are Gunnar, Rutgers group are Mishaikov, and a lot more now. Okay, so everyone is actually in the bandwagon. Okay. So what you want is to extract and understand underlying structure of your data. Okay, all right, so this is the 2 flavors of TDA. You have either, you use either persistent homology or the mapper algorithm. Okay, so later I'll show you some nice application in medical, in math biodata. Okay, so the first is persistence homology, okay, and the other is mapper, but both work on the following. Okay, you convert your data into a point cloud. Okay, actually, this is reconstruction. Okay, the first step is reconstruction data. The second step is converting your data into an object, okay, an interesting object, so that the computer can read it. Okay. And the third step, of course, is interpreting the results. Okay. In persistence, the result is either a barcode or a persistence diagram. Okay. And for mapper, the result is a topological network. Okay. But it's essentially input, okay, converting that input into a nice object, topological object, and then output, either barcodes or networks. Right. So this is the pipeline. Okay. Of course, the assumption here is that, again, what you're observing is something from an unknown space, which has an interesting shape. Okay. So what we want is whether there are topological invariants, okay, that we can that the data possesses. Okay. So by topological invariants, these are just those properties that don't change, okay, whether you stretch, okay, or whether you stretch your space or. So let's see. Okay. So to understand this topological invariant, We start first with the simplest, what do you call this, structure, which is an n simplex. So actually it should be p simplex. So n simplex. For an n simplex, you just need a set of independent points. You have n plus 1 independent points. Okay, and once you have those, you just get the convex hull of those, and that's what you call an n simplex. And here are the 4 simplices for n equals 0, 2, 3. 0, 1, 2, 3. Okay, a 0 simplex is a point, and so on. So once you're done with the simplex, we now go to a simplicial complex. Okay, a simplicial complex is again a topological object which satisfies these 2 conditions. Okay, every phase of the simplex is also in K, and the intersection of any 2 simplices in K, well, you're given the K simplicial complex in K. Any intersection of simplices in K is also a phase of that. Okay. All right. Okay. So at the end, really, what we want to compute here is the homology group. We just really have to go through these definitions. Okay. So once you have K simplex, sorry, it was N simplex, but K simplex is just K plus 1 points, which are independent. Okay. So once you have a K simplex, what you define now is a K chain. A K chain is just this formal sum of K simplices, where the n sub I is from some, the coefficients n sub I is from some set. Okay. In this case, it's Z, but once we go to the application, it's usually Z2. Okay. So out of those K chains, okay, what you want out of the K chains are certain subsets or subgroups. Okay, but before that, we have to define a boundary operator. Okay, a boundary operator acts on an element of CK. Okay, CK is just the collection of all the K chains, and it's called the K chain group. Okay, so this operator acts on this set and brings it to this set. Okay, and this operator what it does for a K simplex is the following. Okay, so it brings it to a K minus 1 chain. Okay, so the hat here means that the ith position is just deleted from the sequence. Okay, so the thing about the kth chain group is that there's a subset of the kth chain group which is mapped to 0. Okay, if you take all of those elements in the kth chain group which are mapped to 0, okay, you call that the kernel of the boundary map, okay, which is ZK. Okay. Also from CK, you have elements D from the C of K plus 1 group, which are mapped to elements in CK. And you call those collections the boundary group, the kth boundary group. Okay, so essentially all of this that we're defining have analogs. The chains are analogs of paths, the cycles analogs of loops, and the boundaries are the analogs of bounding loops. Okay, and there's a theorem that the boundary of the boundary is 0. So in this case, B of K is a subset of ZK. We can define the kth homology group as follows. It's this quotient. ZK over BK is the kth homology group. Okay. And what really, the point of all this really is just solving for the rank of HK. Okay. The rank of HK is called the kth Betti number of your space. And it has the following interpretation. Okay. So for any space, topological space K, you can always solve for the following homology groups. Okay, H0, H1 until H of K. Yeah, so H of 0, H of 1 to H of K. Okay, well, for H of a dimension of H of 0, which is B0, is the number of connected components. Okay, that has something to do with clusters. Okay. Dimension of H1 okay, has something to do with loops okay, or holes, okay, and so on. Okay. For H2, it's the cavity. So if you think of a donut, okay, there's one cavity there, okay, or the tunnel. Okay. H2 is a higher dimensional hole, which is a two-dimensional hole. Okay. So intuitively, BK is the dimension of HK, which is the number of K-dimensional holes. Okay, so we can only visualize this or understand this visually until K equals 2. Okay, so filtration, what is a filtration? This is just a sequence of simplicial complexes so that as you go from Ki to Kj, where I is less or equal to j, Ki is a subset of Kj. Okay, so this is an example of a filtration. As you go to the right, new simplices are added or created. Okay, so how is filtration associate? How do we use filtration in our set of data? Remember, once you have a data, either it's data in RT or a time series that you reconstruct, okay, what you have is just a set of points which are not interesting. Okay, so what you want is to convert a set of points, okay, point cloud data into interesting objects, and this is how you create an object, topological object, out of your set of points. Okay, so you set up a rule. Okay? You set up a rule between points, okay, so that a simplex is created between or among points if a certain rule is satisfied. Okay, right. So in this case, we say use a rule which is given by a Vietoris-Phillips complex. For a Vietoris-Phillips complex or a VR complex, the rule is that 2 points are connected whenever they're within a certain distance. Okay, so you can think of this filtration as follows. At this left end, the epsilon is 0, and as you go to the right, your parameter increases. Okay. All right. So as the parameter increases, suddenly A and B are connected because they're within that distance. Okay. Here, as at some point when the parameter is large and everything is within epsilon distance, then everything is connected. Right. Okay. So what we want from this is to know what properties remain or what properties persist in some intervals of your parameter. Okay, so this is the same similar illustration. Okay, the parameter increases going to the right, and as it increases, some of the points are now within that distance of epsilon. Okay, and so they're connected. Okay, so if 2 points are connected, that's one simplex. If 3 points are connected, then a triangle or one simplex is 2 simplexes created. Okay, and so on. Okay, so this idea of persisting structures, okay, or persistent homologies, okay, is from Edelbrunner, Letcher, and Zomerodian. Okay, so they have a whole theory on persistent homology. Okay, but essentially, really, what we just want is, what's happening is to know what's happening to your space, okay, for all values of epsilon. Okay, so you study all the Vietoris group at once, okay, and whatever structures are created and structures that die, we keep track of. Okay, and how do we keep track of this? In the next slide, we'll show that it's kept track using barcodes. Okay. So this is an example taken from, this is a very popular article in TDA. Whoever wants to study or go into TDA, I really suggest this article by Grice. Okay, so what you have initially, of course, here, which is not shown, is just a set of points. Okay, and suddenly, you know, as you go to the right, okay, you have your rule, which is your parameter. Okay, so if those points are within those parameters, then you just connect points depending on that parameter. So you can see that for H0, okay, which denotes clusters, okay, as epsilon increases, you have, you know, a persistent cluster here. Okay. H1, which is holes, okay, dimension of H1, B1. Okay. You also have the creation and the disappearance of holes. Okay. And H2, which is a tunnel, okay, also appears in this interval. And that's how, simply how to read a barcode. If you take a point, okay, on any line, then that's what it means. At that value of epsilon, okay, there is 2 lines that cross it. So there's two H knots, okay, that appear. There are 2 clusters that appear at that certain parameter. Okay. The other flavor of TDA is the mapper algorithm. Okay. For the mapper algorithm, is I have to be I have to say that I haven't really worked so much on mapper algorithm. I've played with it, but I haven't really done any data analysis on it. Okay, so what you do for mapper is the same. You input a point cloud or data. Okay, and you need the following parameters: filter function and a covering. Okay, a covering for your set. Okay, and lastly is a metric matrix. Okay, so these 2 here are really good software on mapper. Okay. I haven't really worked on the second one yet, but yeah, the first one I've been playing around with. All right, so there's a lot of study now. There's a lot of, you know, fields now, okay, that work on TDA. Okay, lots in the sciences, even biology, chemistry, okay, even machine learning. Okay, it's being used in a lot of fields. So I just want to present, I think, just 3 example applications of TDA. Okay, the first one is with some of my previous colleagues from the Philippines. Okay, one from USA and from Korea. I forgot just one lady here, Dr. Sibayan, Rachel, okay, also from the Philippines. Okay, so what is being analyzed here are is the admixture of marmosets. So marmosets are this. Okay, so they're really cute. Really cute. They look like monkeys. I think they are monkeys. So what we want to analyze is the admixture, okay, of marmosets. So when you say admixture, it's the presence, okay, of lineages in an individual's DNA. Okay, right. So what we did here is we work on the haplotypes of each marmoset. Okay, a haplotype is a good marker for tracking evolution of lineages. Okay, in this case, you know, the data, as Prof. Hurley explained a while ago, it doesn't really come to you ready to input into the software. Okay, so for the data here, our colleague from Broad Institute did all of the pre-processing. Okay, and then our student, Kulan, okay, did most of the coding, okay, to input, to enter it to our software. Okay, all right. Okay, so this is what we use. For each marmoset, you get SNPs. Okay, SNPs are just yeah, so SNPs are the following example of SNPs. Okay, in this case, 2, 4, 6, 8, or 9. Okay, the SNP has length 9, but what we use for SNPs of, I think, at least 1 million. Okay, all right. So for each SNP, you get the homing distance. Okay, between SNPs. And what we did was for marmosets, there are 2 SNPs, one from the mother, one from the father. And so what our data here is actually the following. It's a distance matrix. Okay, the distance normalized, okay, of each marmoset. We had 130 marmosets, thereabouts. Okay. And the input in our in Javaplex was a distance matrix. Okay, so if it's the data that you can't, that's not in RD, it's not a problem. Okay, you just think of another way of extracting a distance between your points, because in this case your points are now in RD. Okay. So what we have is the following. We got summary of barcodes. Okay, so it's not the barcodes that I showed a while ago because the results weren't that interesting. Okay, but here we got summary of barcodes. We got box plots per birth. Okay, so barcode statistics that we use are the following. If X is the birth and Y is the death, okay, that's where the barcode starts, the birth. Where it ends is the death. We can actually get the summary of the following: the mean of the birds, the mean of the death, and so on. Mean, median, or standard deviation. Okay. So we're still trying to get do some stats analysis here, okay, but these are the results for the admixed marmosets and the non-admixed marmosets. Okay. But it's, again, one way of visualizing your data. Seeing that your data is, a set of letters, which is 1 million in length. Okay. Another application of this is on the Zika virus. Okay, so this is a virus from mosquitoes. Okay, and the data here is very simple. It's just the longitude and latitude of where the virus occurred. Okay, and we studied 4 countries: Thailand, USA, Taiwan, and Brazil. Okay, so you can see here that Brazil really had the most number of Zika incidents of the Zika virus. Okay, we used mapper in the middle and barcodes here. Okay, so the red one are the clusters, HO, and the red one are the clusters, and the blue one are the hosts. Okay, so it's very easy interpreting this results. Okay, the red ones or the clusters just tell you the denseness, okay, of the virus, okay, the occurrence. Okay, the more H not you have, then the more dense the data is. And then the H1 is just tells you the loops. Okay, so it tells you actually the loops there correspond to mountains. In this case, if there's a loop, it means that there's it was taken, the location was near a mountain. Aside from that, it's also used, whatever you have from your barcodes can be used in your statistical model. So in this case, they added the features, the H0 and H1 features. So this is a study from Low and Park. Okay, they added the features of H0 and H1, okay, to their statistical model. Okay, so later on in the week, we'll talk about a feature selection. Okay, so in this case, it did show that if you added those features, then you got better accuracy. Okay. All right, and the last here would be application to COVID data. So here you have the COVID data taken from 50 US states. Okay, and this is a very nice tool, the Mapper Interactive. So it compared the results from 50 US states with the highest COVID cases. Okay, and they had 7 statistical measures for each state. Okay, so given as follows. So for the Mapper result, okay, we see the following. So all of this are the Mapper results of the 50 states. Okay, and on this graph over here is just the intensity. So closer to red means that there's more cases, and closer to yellow means that there's less cases. Okay? And from all of this, they only took the top 10, I think. Yeah, they only take the top on, sorry, 10, I believe 10, top 10 cases, okay, which results to this graph over here. Okay. And they compared it to the line graph. Okay. So how is this result in Mapper related to the line graph? Okay. So you can see here that this guy over here, which I think is, I think it's Maryland, Boston, Massachusetts, yeah. Had the highest number of incidents, and that one is this graph over here. It's the one that is away from all of the clusters. So you can, at least, it gives you some understanding of your data, because here is just a line data. The usual stats technique is just line data, but in Mapper, it gives you another way of understanding your data and giving visual results. I think that's it. That's it for my. All right, so the next speaker will start at 12. Thank you for listening, everyone, and we'll see you later at 12. If there are questions, you may type in the chat. Okay, otherwise, see you at 12. Thank you.
Right, welcome back, everyone. Our last session for today is by Professor Emma Rutkamp-Bloem, who is the lead at the Ethics of AI Research Group Center for Artificial Intelligence Research. She's also the head of the Department of Philosophy in the Faculty of Humanities at the University of Pretoria. Thank you very much for being with us today, Emma. We really appreciate your time and we look forward to your presentation.
Hi, okay, I just want to check. There we go. Hi, everyone. Thank you so much for having me. I'm so sorry that I couldn't be there. I was at UJ for 8 years. I really looked forward to being on campus again. But there it is. My third-year babies wrote their supplementary exam this morning. And because, you know, the online environment is so anxious, I didn't want to be on the road if someone had some kind of an issue. So, but anyway, thank you for having me. I made slides and I'm going to talk a lot of them simply because this is, maybe I'm going to use vocabulary that people don't understand completely because this is an interdisciplinary session. And so the way in which I express myself may be foreign or alien to some of you. You can really stop me and ask me, but I won't be able to see if you raise your hand. So if Charas or someone can just say when there is a hand raised and just stop me, please, I would really appreciate it. And I'm also going to ask for some input from you. I don't know you. I can't really see you while I'm sharing my screen. But I really want us to have as interactive a session as possible. So if I ask questions, please try and respond. And we'll try to interact in that way. Okay, so I am going to start off with some questions. Let me just figure out how to do this. All right. So if you look at the screen, just want to take this thing out of my way. Okay, so if you consider these questions, these are questions that you need to have in the back of your mind when you think about ethical concerns broadly in the AI domain. And as you all know today, you know, we talk about AI, we talk about data-driven AI. So let's just consider for a moment, if someone stops you in the street and asks you, what is data-driven artificial intelligence? How would you respond? Would you go into all the detail of Python or something, or would you just have a way in which to explain to them what you think or how it all works, what machine learning is? How would you do it? Would you be able to do it easily? And the reason why I'm asking you this question, and we don't have to have answers to this one, because I think we do all know what it is simply, it mustn't just be a technical application that you're working with. From my point of view, as an AI ethics researcher, as a philosopher, as a policy advisor, it is really important to understand that the AI systems that are researched and designed and developed by members of the tech community should be recognized as socio-technical systems. These systems are not solely technical because they impact on society in ways that no other technology impacts on society. So that's why you need to really go and think, well, what is it that I'm doing? How does it work? Why, so a little bit wider. And that's what I meant with that first question. So test yourself and think, if I were to ask you this question, what would you have answered? But then I want to go to the second question, and here I would really like to see some, if there are any hands, but the horror of sharing your screen is that you are completely in your own space and you can't see anybody else or anything else. But what possible harms to humanity are on the table in data-driven processes in general. Is there anyone who are aware of any of the concerns that have arisen around the use of artificial intelligence in its current context? I would really want to know if there was, tell me if there are any hands or anything in the chat, please. And while you may be thinking of your answer, because I'm coming at you, very fast, just read down to the other questions and think a bit about them as well. What are the benefits for healthcare of data-driven processes? Why should we care about using AI in the context of healthcare? Why should we care about how we model data in the context of healthcare? Is it really beneficial? Why is it beneficial? Then, because it is data that we are working with when we talk about modeling, and we are concerned about humans if we are in the healthcare domain, what do you think data ethics is about? Have you ever heard of it? What do you think it should be about? Just think a little bit about that. Then what specific ethical values do you think should drive data-driven processes in healthcare? We'll come back to this question, so you can put it in the back of your mind through the whole lecture. And then at the end, I'm going to ask this question again. Which values, which principles, which ethical issues is it that you think we should be concentrating on, when specifically in terms of AI health? And whose responsibility is it to ensure that data-driven processes in healthcare are practiced ethically? And who are the stakeholders? More now, the focus on who do you think the stakeholders are, who should ensure that things go ethically, I'll come back to at the end. So I do see 2 comments in the chat, but let me just check if I can see them. I can not. Okay, so these are not questions for me. So anyone who wants to try and answer any of these questions, or just make a comment on any of these questions that I'm asking you to think about. So, okay. Sorry, I'm going too fast for myself. So there's one response in the chat that says, as far as I know, results produced by the current state of AI is heavily biased toward the data fed to it. There have been claims about the blindness of AI regarding some social issues like race or gender. Yes, so one big concern, and we're going to talk a lot about that concern, because I was asked to focus on it, is the question of bias. And you'll see when we get there, we have to understand what do we mean by bias, because bias is a word that is used in different contexts, in different disciplines. It is the case that if there's any kind of skew in the data, given the way in which machine learning processes work, that kind of skew, if it becomes a pattern, will be amplified. And so if it is if it is a harmful skew, obviously the harm would be amplified then. But whether this is an intentional thing and what we can do about it is what we're going to be talking about a lot more. There are other concerns as well. One concern is, for instance, we don't know what children, that are growing up in the age of AI will be like as adults. We don't know what the impact is on if it's beneficial or not beneficial, or if there is a mix, or we simply don't know how they will be as adults, obviously. But then there are also obviously wider concerns around inequality, widening the inequality gap. In terms of access, all of us in the pandemic now realize just the digital divide, never mind the AI technology divide. And then there are also, of course, issues around privacy of data, accessibility of data, revising one's data, the right to be forgotten, those kinds of concerns. So there is a whole host of concerns in the ethics of AI, but specifically in healthcare. Is there anybody who would like to venture some stab at what you think specifically in the context of healthcare, what would be a concern? Okay, yes. So there's in the chat, data-driven processes help the healthcare provider, I suppose, to improve patient care, to adopt better technologies. It could. So I think it's something that, from my perspective as a philosopher, we very seldom make like blanket generalizations. And if we want to be concerned about the impact on humans, then we would, it's better to say, well, okay, obviously we are looking into AI applications in healthcare because we want to improve patient care and we want to improve our knowledge of disease in general. But so if all these processes happen in ethical ways, then it would improve patient care as a blanket statement. But if these processes do not happen ethically, then, you know, is maybe a better word. It may improve patient care to some degree. It can aid well-being. Data-driven AI can aid well-being. It can also be completely detrimental to well-being. But you're right, that is why we are interested in it in terms of healthcare, because we hope that it can benefit patients and contribute to their well-being. So are there any other, does anybody want to venture a thought on what data ethics is before we continue? Okay, I'll ask you again when we get to this slide. Maybe you can think a little bit about it. If I remember, I'll stop at the title of that slide, and then we can get to it. So what I'm going to do now is to move to the next slide. Okay, right. Just in terms of the lecture, I'll give you a bit of background on AI and healthcare. I'll tell you, and we will discuss a bit what data ethics is all about. Okay, I'll just go back to the chat quickly. There is one more comment. Data and healthcare is likely to have new risk issues from Zulani. Firstly, who and how they access medical information, what that information can be used for, knowing one person, for instance, knowing one person's allergy can be used in causing an allergy, not just treat an allergic event, so on. Okay, all right, yes, there are new risk issues. There is potential for enhanced quality of care through tailored or differentiated care. However, there are risks of enforcing the biases inherent in the collected data and processes of collecting data. Data security also prevents such issues. Yes, so we have to be very concerned about the quality of the data. In any AI, data-driven AI process, the quality of the data is prime, okay? And data ethics concerns itself with that, but from an ethical point of view, not from a technical point of view. Okay, so we'll talk about data ethics then a bit, and then we will specifically focus on what fairness, bias, and non-discrimination are all about in data ethics. Then I'll say a few words about biomedical ethics, because what happens when we talk about ethical concerns in AI healthcare, AI applications in healthcare, is obviously that we are merging data ethics with biomedical ethics. So I will give you a bit of background about what biomedical ethics is about, and then we'll focus on ethical concerns in AI health. And I'm going to focus just on one article because this is all new to you. And I'm also going to share the article with your lecturers at the end, just after I'm done, so that it can be shared with you. You can also look at the article. So we'll talk about some ethical concerns, and we'll focus on epistemic, normative, and overarching concerns. And this is an article in Social Sciences and Medicine that I'm going to be focusing on. Then I'll just flash a few mainstream policies on AI applications in healthcare, because there are quite a lot. And you will learn a lot more about ethical concerns if you go and scan some of these, and they are really, they're freely available. You can download all of them freely and find them easily on the web. Then we'll consider what should an AI health ethics look like? What would we want such an ethics to be concerned about? and how ethics could enable responsible research in this domain. Okay, so let me get cracking. I forgot to number my slides, so I hope I stay in time. I'll do my best. So please alert me if there are any hands. I can see if there is a message in the chat theoretically, but the hands are not that easy. So, okay, AI in healthcare. So globally, healthcare systems are struggling with increasing costs, with case overload, and far from ideal outcomes. This is not necessarily a new thing, but I think it was more put in our faces because of COVID. We became more aware of it because of COVID. But this is an ongoing issue, and this is not an issue that something, or these things are not only issues in South Africa or in Africa as a continent. These are global concerns in terms of healthcare. And the problem with this is that there are many diverse causes for this globally shared problem, and that makes it hard to define, and it points in fact to many diverse approaches to finding solutions because there are diverse causes. So sometimes people are talking across each other, and they forget maybe that they have to think about the patients as well. So we're at a difficult stage in terms of healthcare. But what is shared in all these solutions, in fact, is that from policymakers to data scientists, the implication is that somehow a key part of all of these solutions will be artificial intelligence, and in particular, machine learning processes. So the idea is that what is needed, and quoting Morley and Floridi, is that we need a more informationally mature and heterogeneous organization, reliant on data-based and algorithmically driven interactions between human, artificial, and semi-artificial agents. So somehow we have to get a grip on information in healthcare. We have to get the organization to be more streamlined and heterogeneous. And we have to understand that we need to have algorithmically driven methods to make sense of the information that we have, because the information is so vast. So such hybrid or AI clinician cooperation includes, for example, using decision tree techniques to diagnose breast cancer, support vector machine techniques to classify genes and diagnose diabetes, ensemble learning methods to predict outcomes for cancer patients, and neural networks to diagnose stroke. So from this perspective, Morley et al. Write that AI represents then a growing resource of interactive, autonomous, and often self-learning agency that can be used on demand, presenting the opportunity for potentially transformative cooperation between machines and doctors. Now, the autonomous part is one of the issues that we can at the same time be very excited about and also very concerned about. Because whenever we think about healthcare, we want to obviously take the person who's in fact ill and very vulnerable into consideration. Right, so, but if we harness this kind of resource effectively, Morley et al. Claim that such AI clinician cooperation, where AI is used to provide comprehensive, evidence-based clinical decision support, and this is what AI health means. If we use this effectively, it could offer great opportunities for the improvement of healthcare services and of patients' health. So just be clear on the definition. AI health is using AI systems in combination with human clinicians to provide comprehensive evidence-based clinical decision support to the human clinicians. But if these AI solutions are embedded in clinical practice, then we need clear and responsible governance. We need to make sure that no one is harmed, and we need to make sure that no unethical conduct specifically is harming anyone. And not only patients, of course, but also practitioners themselves. So ethical concerns must then be taken seriously. Why? I mean, what is now this big thing? I mean, you know, stuff happens, you know, what? We can't make sure that everything is fantastic just because it's healthcare. But there are two reasons for this. And it has to do with what Cookson calls opportunity costs. So if too many mistakes are made, it can lead to social rejection or distorted legislation and policies and crippling acceptance and advancement of data science. So in a nutshell, one doesn't trust, one doesn't adopt a technology completely if one doesn't trust it. And given the nature of AI systems and data-driven AI in general, if these technologies are not adopted fully, they cannot be realized to their full potential. And that will then just snowball into more distrust and less adoption. And there we go. So it is extremely important, not only from a social science point of view, and people jumping up and down and say, remember the humans, not only from that point of view, I'm not belittling it. I'm trying to you know, to make the point that that's not the only thing that is an issue. What is also an issue from a business point of view? It is very important, and from a research point of view, it is very important that people actually trust these technologies and that they're adopted in the right way. So jumping up and down about humans can become something that is easily ignored, and that is why I use those words. But if we understand the widespread consequences of not thinking deeply about the ethical issues that immediately are raised when we apply AI technologies in health, then we understand how important it is to jump up and down about the humans. Okay, so then, but where do we turn? So this is now really important and everything, but where do we turn? So there are bioethical and biomedical principles for clinical research that are well documented and accepted. Have been well debated, well discussed for, in fact, quite a few decades. So we can start there. But at the interface of AI and healthcare, there are other concerns that muddy the water, such as opaque data-driven practices, bias, discrimination, or even mistakes in decision-making. And this brings me then to, now we first have to consider what data ethics is about, because these are issues that muddy the waters, that cause us not to be able to use the already established bioethical principles. So if anybody wants to say something about what they think data ethics is, now is your moment. Okay, I'm going to push on a little bit. So data ethics is centered on issues around fair, accountable, and transparent machine learning, FAT machine learning, known in the colloquially in the domain of critical machine learning. Fairness, accountability, and transparency are big issues in data ethics, as are socio-technical analyses of machine learning practices and their impact on society, and then responsible data governance. The governance isn't necessarily part of considering the impact, but if one is researching and designing an AI system, one has to consider the moral and social consequences of the predictions that will be generated by that system. So as such, then, Floridi and Tadeo defines this branch of ethics as the domain that studies and evaluates moral problems related to algorithms and corresponding practices in order to formulate and support morally good algorithmic solutions. So it is about not harming anyone in the process when one works with this wonderful technology, but at the same time understanding and being sensitive to the fact that this technology can actually do a lot more harm than good if it isn't governed responsibly. So some of the fact concerns and the fairness, accountability, and transparency. I'm going to focus on fairness most, but just 2 words or 3 words about the others as well. So in the ethics of AI and the wider machine learning community, recently there's really been more and more calls in the ACM community as well for a turn to critical machine learning, with emphasis on fairness, transparency, and accountability in general, but specifically focused on autonomous decision-making systems that are powered by deep neural network research and technology. So fairness usually refers broadly to accessible and reusable data, but it also includes concerns around structural bias, and I'm going to say a lot about that in what comes. Transparency refers to making the processes of the system visible and explicable, and it includes informing users when machine learning driven processes are used. You have the right to know when an algorithm has made a decision that impacts on your life. Okay, that's what transparency is about, as well as knowing and making visible the processes of the system. It relates to understanding how machine learning systems are designed, developed, and deployed, while explicability or explainability, which is the like Siamese twin of transparency, while this also relates to understanding the outcomes of these, and it also relates to interpretability. Okay, so it's understanding what is happening, how does the system work, and being informed that the system is actually in play. Accountability relates to ascribing ultimate human responsibility for the outcomes produced by machine learning systems, and the auditability and traceability of the workings of such systems, and is thus in that sense closely related to transparency. It also relates to the consideration of ethical questions, such as, for instance, should there be blanket disclaimers of liability allowed in this kind of technology, or only, for instance, for systems that affect the quality of human lives directly. So if one wants to allow disclaimers, what kind of disclaimers in terms of liability would one allow? And what does affect the quality of human lives directly even mean? Who will decide which systems affect the quality of human lives enough for it to be excluded from blanket disclaimers? So these are all really important questions that we are all looking for to answer. So if we now focus specifically on fairness, bias, and non-discrimination, what does bias mean? It has different meanings over time and in different disciplines. Okay, so in the statistical sense, it relates to systematic differences between samples and populations, as I think all of you know. In the legal sense, it relates to prejudice and the objectiveness of impartiality, or the non-objectiveness of impartiality, because if we talk about bias, we're saying we're not being objective. Now, in the social sciences, it refers to what is referred to as structural bias. And this has to do with the fact that data may be private or otherwise sensitive because, given how human societies are structured, it may contain some ideological or other forms of identity prejudice, which leads to structural bias. So if this kind of bias is embedded in data, it relates then, for instance, to gender or race, or ethnic or age-related biases. So broadly to data somehow inherently linked to prejudice based on social identities. And social identities are humanly constructed identities based on social power. So understanding structural bias and its consequences for action based on the outcomes generated by systems that contain biased data is necessary to ensure the fairness of machine learning practices. If we are not sensitive to possible structural bias in the data that we use to train our systems on, then we cannot claim that our practices or our systems or our processes are fair. Okay, so fairness always relates to bias in this way. And so obviously, from what I've said already, and I've talked about social power and social identities and things that I don't think, as a matter of course in your work, maybe consider a lot. So obviously, this phenomenon has to be analyzed in an interdisciplinary manner. It is not something that the tech community has been trained to consider. Because, for instance, an unbiased system in a machine learning sense can produce the biased result in a legal sense when a model is reproducing biases because it was trained on data sets that reflected structural inequalities. So one has to, the technical community in their research, design and development must consider the moral consequences of what they are building, and they have to consider the building blocks, which is the data. But they are not necessarily trained to do that, and therefore they cannot do this in optimal ways. And that is why we need, in any kind of ethical consideration to do with AI, we need inter and transdisciplinary work. So this is the real concern, and what we should be sensitive to, that there are social factors that can impact the success of your AI system. It is not only about the technical aspects. But where does this unfair structural bias come from? It's societal, as I've said, social power closely linked to identity prejudice. But then there are also aspects of any person who is collecting data and training a model is a human with human biases themselves. And of course, they are collecting data that was generated by humans in a human context. So the processes of data collection and processing, the choice of machine learning system and modeling itself, in fact, all these processes also create structural bias, or can magnify it, can amplify it. So if we very quickly look at these aspects first, then we're going to go back to the social concerns, because I'm not here to give you a technical talk. I'm here to give you a more social kind of focus on these concerns. But unfairness in categorization, data collection and processing refer, for instance, to the fact that scrubbing to neutral has subjective elements and is no easy task in a messy world. Barker and Starr's book is a fantastic book on this. Target variables are in general constructs, not measured or well-studied concepts. For instance, creditworthiness isn't a property one has or does not inherently have. It isn't a concept that is well-defined. It's a constructed concept for particular purposes. So of course, there is already some kind of value judgment, if not bias. The neutrality fallacy is dangerous. Machines will not sort messy things out just because they are objective. Or supposedly so. So the high demand, another example, the high demand for label data in the context of supervised machine learning specifically can only be met if data from previous decision-making is used. But then we may be replicating historical bias and prejudice that we may not have been aware in the previous case. Then also, if there is historically less data on some groups, models may reflect this differentiation too. Sometimes there are other proxies for discrimination, such as geography or race, of which we're not consciously aware of when we look at the data. So if you think of the NYPD stop and frisk program, that they stopped and frisked more African-American persons that actually live in New York during the time that the decade that this program was at work. So every single person who just happened to be there was in danger of being stopped and frisked because of the algorithm they were acting on. Postal codes, for instance, also has proxies for discrimination. And sometimes these are used to determine credit scores for online companies and delivering companies and so on. And then lastly, something, maybe a little bit deeper, what we really have to think about this is that assumptions that the real world is binary or discrete, and that data sets come with a predefined ground truth label for each example, which relates to some of the higher up things that I've said already, presuming that a true label always exists out there, independent of who is designing it or carving it out or defining or labeling it. Such assumptions go against calls from marginalized scholars for machine learning models that allow for non-binaries, for plural truths, for contextual truths, and many ways of being. So it isn't the case that there is just one way in which to label a data set. And we have to ask ourselves, what is it that is driving our decisions when we do such things? But I want to continue if my slides allow me. Unfairness of selection and specifying a machine learning system. There is obviously subjectivity of system design and deployment. There can be any kind of values that can impact on one in that process. And then there's unfairness in categorization modeling. Patterns will be recognized. Those we want to see, such as that smoking causes cancer, and irrelevant stereotypes such that girls like pink. Absent specific intervention, Barakas and others say, absent specific intervention, machine learning will extract stereotypes, including incorrect and harmful ones, in the same way that it extracts knowledge, and we have to be aware of this. Disparities, also another factor that we have to take into account here. Disparities not present in training data may also nevertheless be introduced due to uniform sampling from training data, which implies fewer data points about minorities. And so if we're not careful, learning algorithms will generalize based on the majority culture, leading to a high error rate for minority groups. And in healthcare, this is really dangerous. And then, of course, feedback and feedback loops. Feedback has to be interpreted carefully so that we don't carry over historical bias. But, you know, I mean, the nature of machine learning is to discriminate. So we use machine learning systems to distinguish data points from each other based on certain predictive characteristics. That's the whole point. That's the whole beauty of machine learning. So, you know, what now? We have to simply be sensitive to the fact that the problem with addressing bias is twofold in character. We have to find the right computational mathematical mechanisms to address the bias that emerges from complex socio-technical systems, not like AI systems are not just technical, as I've said. So we have to find the right computational mechanisms, and there's a number of open source methodologies available already that can help you detect bias and evaluate fairness of your systems. But at the same time, we also have to find the right social science mechanisms to address the bias that emerges from these socio-technical systems. And here we have to acknowledge the effect of social power on the quality of data and machine learning practices in general. And we have to acknowledge that machine learning does play a role in harmful representations of human identity. And we have to be sensitive to that. Now, Crawford, I'm going to skip this slide, and you can come back to it, but she warns about two kinds of harm that comes from machine learning: allocation harm and representational harm. So simply, it is the case that we reinforce subordination of certain groups through machine learning practices, or we allocate certain things to only certain groups because of machine learning processes, because of structural bias in machine learning processes. So, you know, the famous example of Google Photo identifying African American men as gorillas, HP camera not being able to recognize Asian faces, some speech-to-text technologies not recognizing female voices. There are many examples of the horror of the harm that can come from desensitized machine learning processes. So structural bias relates to classification practices. We have to represent the world as it is, but then discrimination is likely to stay put. So do we change the representation when we classify to fit things as we think they should be? But then who decides? Who are you to decide how the world should be classified? Whose idea of neutrality is at work? So it has to do with being sensitive to the fact that how we represent culture and historical divisions in society is a problem when we work in data-driven processes. So I'm not going to look at all of what I've said here, but we have to understand that we need to identify relations of power and privilege that sustain injustice if we want to have fair machine learning practices, and that this cannot be done by the tech community in isolation of social sciences who are trained to pick up these forms of injustice and who work very hard to try and counteract them. So we have to think about the ethics of classification. We need social system analyses. So we can't just, like, you know, an example is the risk cause in criminal justice, for instance, using algorithms to decide who gets bail and who don't. And these are really, I mean, everywhere in practice already, or quite prevalent, let me put it that way, or prevalent in the United States. And then you see it's the same nationalities and the same race and gender that consistently do not get bail. But their social context is not taken into consideration. Do people maybe have children that they can't leave at home? Do they have money to commute back to the court? All kinds of these kinds of issues. So we need a fairness forensics also. We need to have pre-release trials. We need to be sensitive. We have to do everything that we can to understand the skews of our data sets. And we need data activism and data activist research. And this is the idea that machine learning practices should only be allowed to have an impact on communities if they are going to benefit, if they have proven benefit for those communities. And people like Timnit Gebru, who was the ethics lead at Google and who were famously fired last year in December, go and Google her. These people like her are really very adamantly fighting for these kinds of things. But we are here to talk about biomedical stuff. And we're here to talk about data and healthcare, so back to that now, against this background. So just quickly, in terms of biomedical ethics, the established principles of healthcare ethics: autonomy, justice, beneficence, and non-maleficence, the do no harm principle. So in terms of autonomy, a patient should always be fully informed, should have autonomy in terms of reasoning, intentions, and actions when making decisions regarding their health. In terms of justice, there should be equal responsibility for healthcare decisions. Resources should be evenly spread. Think about AI application. Resources should be evenly spread. Competing needs should be considered. And of course, you have to comply with the law. In terms of beneficence, of course, everything that you do should always be with the patient's best interests at heart. And then there's the do no harm principle. But these principles are wonderful, but because the social sciences are not, you know, like there isn't just black and white in the social sciences, which is really something that is upsetting maybe to people who come from the mathematical sciences. There are conflicts among these principles because we're dealing with humans. So sometimes even beneficence and do no harm can be in contrast with each other. And then one needs to have ethical reflections and debates and decisions. So already, even in the established domain, we have problems. So if we then now turn to AI health, and I'm leaving this table for you, it's too small anyway to see anything on it, but I just put it in the slide so that you can look at it later on. This is now from the article. Here I'm going to focus only for the next few slides on this article in Social Science and Medicine from Jessica Morley and her colleagues, where they identified epistemic, normative, and overarching concerns in AI health. So epistemic concerns, very fast, relate to that there may be misguided trust in the truth-telling power of AI health. Algorithms can process more data relating to factors such as demographic and socioeconomic status, system and existing diagnosis data, treatment data, and so on. So of course, algorithms are better than humans in terms of processing data. And algorithms can also take evidence-based decisions that outreach that of human medical practitioners, as far as analysis of risk factors, prediction of adverse effects, outcome of likelihood of survival, and analyzing electronic health records, and so on. But in AI health, Morley et al. Write that we have to consider that existing methods and studies suffer from overfitting due to small numbers of samples, meaning that the majority of results are inconclusive. Data in health is in any way, accessibility of data is in any way very, very problematic. And this has an influence on the processes. So this is a problem that is further magnified by the lack of reproducibility and external validity of results. And AI health solutions are often untranslatable between different settings and rarely work in settings different to those in which the initial result was obtained, raising serious questions about the scientific rigor of AI health and its safety. Furthermore, the results can often be heavily value-laden based on the definition of healthy by influential people or powerful private companies. So ethical concerns at the individual level, there's a risk of misdiagnosis. At the group level, decisions based purely on categorization may lead to group profiling and associated discrimination. So if we only look at how algorithms are categorizing people, we lose the human aspect. At interpersonal level, patient trust in medical care may suffer if it is solely or mostly based on quantitative and objective evidence. Objective, for all the reasons we've just said, so objective in inverted commas. Other forms of treatments not driven by clinical algorithms may even be discredited. And at the institutional, sectoral, and societal level, it may lead to wasted funds, poorer healthcare, undue sharing of patient data, and so on. So the epistemic concerns are quite concerning. Okay, they're quite serious. Now, the normative concerns, Morley et al. Write that whilst it would be ethically remiss to ignore opportunities to address existing concerns in healthcare via AI health, it would be equally ethically problematic to ignore the fact that these opportunities are not created by AI health technologies per se as such, but by their ability to fundamentally change the intrinsic nature of the ways in which healthcare is delivered by coupling, recoupling, and decoupling different parts of the system. And I'll tell you what these are in a minute. So it's about changing the ways in which healthcare is delivered, okay? And this changes because this changes the affordances and constraints of different governing bodies, regulators, and system agents, undermining the mechanisms in place to hold those delivering care accountable, and thus introducing new risks, as some of you mentioned in the chat. So coupling has to do with the fact that patients become data subjects. So a patient becomes their data. So there is this implosion of data and humans. Recoupling has to do with the fact that suddenly medical research and practice are married again. They've been apart for many decades, and the ways in which we have been governing medical practices took this into consideration, but suddenly they are very close together again. And decoupling has to do with the fact that healthcare, in the healthcare context, the healthcare providers and the patients do not have to be in the same space. And again, our legislation isn't geared towards that. We very much are focused on in-person contact. So ethical concerns raised at this level, at the individual level, as individuals share more and more data, they may become less and less involved in their own actual healthcare process, due to the possibility of opaque use of their data. They may not even be aware when AI algorithms are taking decisions, and they don't understand how they make those decisions. This may impact on their sense of self and feeling of being in control, as they may not understand all the forces acting on them. And this transgresses the biomedical principle of do no harm, as well as the principle of autonomy. At interpersonal level, healthcare providers may feel out of the loop in their turn, as patients and their clinical algorithms take decisions, in a sense, excluding the human healthcare provider. Clinical practice is complex and involves dynamic interaction with the patient and medical literature, which are not necessarily part of AI health solutions. And as such, these practices may therefore not be in accordance with current best practice. But best practice is necessary to handle the great degree of uncertainty and can only be fully evaluated by physicians. At the group level, if diagnosis and treatment are left solely in the hands of AI health, groups that are not well represented in terms of available data, such as Black female patients, may be misdiagnosed. Possible structural bias in data sets may lead to funds being allocated to the same groups over and over, and thus sustaining inequality in healthcare. And at the institutional, sectoral, and societal level, it is really imperative that institutions decide how much clinical decision-making should really be delegated to AI health solutions. And this is a decision that should be taken about the role of healthcare in the context of the role of healthcare in upholding or ensuring social justice. So healthcare isn't given to, isn't, offered to people in a vacuum. It is in a particular social setup that it is offered. So we have to think wider. Again, the need for interdisciplinary thinking, really important here. And in terms of AI health in the private sector, the broader risk of privately held AI solutions is worthy of caution going forward, and a worthwhile topic of ongoing discussion in public health ethics, because data is generated about the public by public actors, but then given to private companies. And we need to keep an eye on that. Society should also reflect on and decide what constitutes basic and good care before deciding on the role of AI health in healthcare, and the public should be involved in designing of AI health systems. And this is something that the UNESCO policy, that I'll say 2 words about in a minute, also is really very adamant about. So in terms of overarching concerns, healthcare systems now rely on a dynamic, cyclical, and intertwined series of interactions between humans, artificial, and hybrid agents. But this is making it increasingly challenging to identify interaction emerging risks and to allocate liability, raising ethical concerns with regards to moral responsibility. So Morley et al. Write that in a well-functioning healthcare system, this responsibility is distributed evenly and transparently. So this is the biomedical principle of justice. But in an algorithmically driven healthcare system, transparent allocation of responsibility is difficult. Not only is the decision-making process of a single algorithm a black box, but the entire chain of actors that participate in the end product of AI health solutions is extremely complex. So here, ethical concerns at the individual level. If individual patients, for instance, do not follow AI health instructions, such as monitoring of symptoms, their treatment may not be successful, and they can think it's their fault. But it could very much be the fact that the device that they are wearing, or whatever the case may be, is in fact not functioning optimally, but there's a lack of traceability that muddies the waters. So it is difficult to say whether this is a technical or a human issue, and then we blame the human. And we also have to consider that, do we want algorithms to then hand out blame? So it's your fault. You don't understand how your watch is working. Your Apple Watch is tracing your steps or whatever. It's your fault that you are not getting fitter or whatever. Is that really what we want? At group level, problems of traceability may also lead to a risk of undue discrimination and biased data sets, as healthcare monitors do not work equally well on all members of all demographic categories. At institutional, sectoral, and societal level, there are liability gaps. So, right. Now, I'm not going to say much about these mainstream AI health policies. So we've discussed now the ethical concerns around AI health in terms of epistemic, normative, and overarching concerns around moral responsibility and traceability. But I also want to make you aware of the fact that there are many policies available. There's the Digital Europe Microsoft policy, the Wellcome Trust policy, UNESCO's International Bioethics Committee report, the Nuffield Council on Bioethics, really respected entity. And in all these kinds of policies, there are, at least the focus is on some shared principles: transparency, fairness, accountability and responsibility, and privacy. The UNESCO recommendation on the ethics of AI also has a policy area that is focused on health and social well-being, so a whole policy area just dedicated to this. And when you read it, I'm not going to read it for you, but what is really important is that the patient should be empowered to play a role, and the patient's relationship with their family, and not only with healthcare staff, should play a role. That, of course, bias should be minimized and mitigated. Of course, we should be within data protection requirements in terms of patient data and all of that. But then also humans should be the ones who take ultimately decisions about healthcare and in terms of a patient's treatment. And there should be ethical committees that review the use of AI systems prior to clinical use. So you can go and read some of these if you have nothing to do over the weekend. But now, just in the last 5 minutes, and I'm sorry that I'm a little bit over time, but I want to also have 2 minutes for questions also. If you were to think in your head, which principles do you think should be included in AI health ethics? And who do you think is responsible to ensure that we have ethical AI health practices? And what would happen if we don't? If you want to think about this for 1 minute and maybe say 1 or 2, if you have a comment in the chat that you would like to share with us, which principles do you think we should be really or non-negotiable in AI health ethics? Who should, is it the administrators of a hospital that should take care that these processes are ethical? Does the patient have any kind of role to play? What is the role of private companies that develop these systems and applications? Shouldn't they also have some responsibility to ensure that what they are producing is ethical, as I've been trying to show you all the time? We have to be aware of these kinds of issues from the research stage, through the design, through developing, through deployment, and into use. The whole system of an AI, life cycle of an AI system should stop and wonder about the ethical concerns, but who should be doing this? Okay, I'm going to continue because nothing is happening in the chat, but I hope that you will ask me questions about this then in question time. So my suggestion for principles should be the 4 biomedical ethics principles: autonomy, justice, beneficence, and non-maleficence. The FAT principles: fairness, accountability, and transparency. Privacy concerns, obviously. You should have access to your data. You should know where it's stored, who have access, how long it would be stored, the right to be forgotten, all of those issues. And then responsible, adaptive, and multi-stakeholder governance. And the values, I think I just want to say just a little bit about values that should be underpinning these principles. So I wrote the human rights and duty to the community. So one thing that we have to be very careful about is in the bigger domain of AI ethics, the principles and values that we are faced with or confronted with are mostly generated in the North. The South is, for all intents and purposes, excluded from most global AI ethics conversations. And I know what I'm talking about. I can tell you, UNESCO was my first experience where there were actually people from all over the globe present at these discussions. So what happens is, in the North, in the North, there is people work within individualist ethical systems. Here we work within collectivist ethical systems. So in the North, policies, it is just natural to formulate ethical concerns and then policies to address those concerns in terms of individual rights. And of course, all of us have to comply with human rights standards and principles because it's part of international law, and we all have to comply with international law, and no one is disputing that. But in the South, because we work within collectivist ethics, communitarian ethical systems, our focus is not so much on the rights of the individual as the duty towards the community. So we have duty-based ethics, not rights-based ethics. And so when we think about AI health ethics in South Africa, we have to be very sensitive that we frame what we say in ways such that the people who have to adopt these policies and ensure the benefit of patients, that they can actually, that they feel that they know the vocabulary, and that they feel that their values have been taken into account in some way. So I can say a lot more about that, but I think it's just important. Last slide, how can ethics be an enabler of responsible research? We have to recognize that ethics is a constant ally and companion on this road to harmonious, innovative, and responsible AI health context. It isn't an add-on. We need an active understanding of ethics as a dynamic system of values. You don't decide forever and ever what the right thing to do is. You rethink your actions all the time as a human being. Ethics is not a static system, and it simultaneously accompanies and is informed by all AI actors throughout the life cycles of AI systems. And AI ethics must deal with the fact that people's thinking about ethics changes as human society and technology change, and ethical concerns themselves change as a result. The only way to protect the integrity of research and innovation in the sense of benefiting humanity is then to rethink ethics as being inside both societal and technological practices, enabling just and effective AI health context in a co-shaping relationship with humans and technology. We cannot take the two apart, and we cannot have ethics outside that kind of co-shaping relationship. Ethics is part of all of it and should be what in fact drives this kind of relationship. And for that, we need cross and transdisciplinary research. So thank you very much. I'm going to stop sharing my screen and be quiet. I'm 1 minute over time, but I hope there is maybe time, a few minutes for question. Yes, Kevin says that aside from the 4 biomedical ethics principles, we should include explainability. And I agree, but explainability is part of the FAT principles, the part of transparency, but you're completely right. It's very important that people understand how decisions are made about how their health is treated. Definitely. Thank you.
Thank you, Emma. I don't see any other questions, but yeah, I'm pretty sure Emma will be willing to respond to any emails if there's any burning questions around ethics required from any of you. I just want to thank you so much. I know you wanted to be here, and we appreciate at least that you're with us online. So thank you so much for your time. It's really been a pleasure having you as part of the workshop.
Thank you. Thanks for having me. I'll send you the slides. And I'll send you the articles, maybe 1 or 2 articles related also to what I've been saying. And anyone in the group who is interested to speak to me, you're very welcome to communicate with me. Thank you.
Thank you, everyone. So that is our last presentation for the day. So for those of you that are with us online, thank you so much for being with us. And hopefully we'll see you all tomorrow. For those that are here with us in person, there will be a lunch now, and then this afternoon we will start our workshop. So thank you so much. Have a good day, everyone. Thank you.